Hello there and welcome to Life Beyond Seen, where curiosity slows down, science leans back in its chair, and we let wonder keep us company for a while. Tonight our attention drifts not upward towards stars but downward into shadows, into a place most of us will never see with our own eyes, and yet, somehow, it feels closer to us than distant galaxies. We're going beneath the waves, into the deep sea, a world that has quietly held on to more mysteries than outer space itself. Strange, isn't it? We send probes to Saturn's moons, we photograph galaxies billions of light years away, and still, the oceans on our own planet remain largely uncharted. It's as if Earth is politely keeping a few secrets from us. Before we sink into this hidden world, I'd love to know, where are you listening from tonight? Are you near a coastline, where the air carries a saltiness that drifts in through your window? Or maybe you're hundreds of miles inland, with oceans only ever appearing in postcards, screensavers, or long-ago vacations. Either way, the sea surrounds us all in ways we rarely think about. It regulates our weather, shapes our continents, and quietly provides the oxygen in our lungs, and yet, for all of its importance, it's also the least understood realm we have. That, perhaps, is part of why it calls to us. If this journey feels like something worth drifting into, a way to let your thoughts slow and wander after a long day, I'd be grateful if you'd give the video a like, maybe even subscribe. It helps more people find this little corner of calm curiosity. And with that, let's take a deep breath together, as if preparing to dive. Because once we leave the surface behind, everything begins to change. When you think of the unknown, of mysteries yet unsolved, most people picture outer space. It's the default image of the unknown, black skies littered with stars, worlds beyond our own, distant galaxies. And yet, the truth is that we know far more about space than we do about the ocean depths. Scientists estimate that we've explored maybe 5% of Earth's oceans. 5. If your teacher gave you back a test with that score, you wouldn't brag about it. And yet, that's where humanity stands with the seas that cover more than 70% of our planet. Compare that to Mars, where we've mapped the surface in extraordinary detail. We know the layout of the Martian valleys better than we know our own ocean floors. The same goes for the Moon, mapped down to individual craters. Satellites can see through billions of years of space but can barely penetrate a few miles of water. The irony is striking. Part of the reason for this imbalance lies in the nature of water itself. Light doesn't travel far beneath the surface. Red fades first, then orange, then yellow, until by the time you reach just 100 meters down, you're in twilight. Beyond that, the dark thickens. Even the strongest beams struggle against it. Space may be vast, but it's open. Light travels easily in a vacuum. Water is different. It swallows light, muffles sound, and grows heavier by the meter. That weight is another problem. At just 1 kilometer below the surface, the pressure is 100 times what you feel on land. Go deeper still, and it's enough to crush steel. This is why we can't simply strap on scuba tanks and wander into the abyss. Every meter downward is like stepping into another planet's environment. It's tempting to think that because oceans are on Earth, they're familiar, but they're not. They're as alien as anything we imagine among the stars. That might be why we keep comparing the deep sea to space. Both are hostile to humans. Both are filled with environments we weren't built to survive. And both hold out the promise of discoveries that could completely reshape our understanding of life. The difference, of course, is that the deep sea is right here. You don't need to wait for a rocket launch. You just need a vessel capable of surviving the crushing depths. And yet, that's proven just as difficult as leaving the atmosphere. Imagine yourself in a submersible, one of those small vessels designed to descend slowly into the deep. The surface above grows fainter. Sunlight shrinks to a shimmer, then disappears entirely. Instruments glow in the cabin, reminding you that outside the glass, it's a darkness so complete it feels almost physical. This is the deep sea's great disguise. It hides itself behind that darkness, behind pressure, behind silence. Not many places on Earth can make you feel like you've left Earth entirely, but the ocean depths can. And that's why we say the deep sea holds more secrets than space. It's both within reach and forever, just out of reach. It's worth remembering how little of our history has involved looking downward. For centuries, sailors treated the ocean surface as something to cross, not something to enter. The depths were dangerous, unknowable, often the subject of myth. Sea monsters, krakens, mermaids. These stories weren't just entertainment. They were reflections of how humans felt about the ocean, a mix of fear and awe. Meanwhile, our eyes and imagination were turned upward. The night sky was visible to everyone. You could chart it with nothing more than your eyes and maybe a simple telescope. You couldn't do that with the sea. To know it, you had to enter it, and that was something most people couldn't do. Even today, with satellites and sonar, most of the ocean floor is mapped in only rough detail. Entire mountain ranges remain unstudied. New species are discovered regularly, sometimes by accident, reminding us that the sea is still a frontier. Think about that for a moment. In a world where you can pull up a map of nearly any street corner on your phone, there are still massive parts of Earth that remain unmapped. That contrast is staggering. It means that within the same planet where we live our daily lives, order groceries online, and scroll through social media, there exist worlds untouched, unseen, unexplored. The deep sea is proof that mystery hasn't vanished. It just hides where most of us never look. Part of the challenge comes from how hostile the deep ocean is to technology. Spacecraft face extremes of cold, radiation, and distance. But the ocean brings its own obstacles. Pressure rises by about 1 atmosphere every 10 meters you descend. At the depth of the Mariana Trench, nearly 11 kilometers down, the pressure is more than 1,000 times what you experience on land. That's enough to collapse most structures instantly. Submersibles need to be built like fortresses, with spherical cabins made of thick steel or titanium, sometimes with windows no larger than dinner plates. Sending a person there is a monumental task. Even sending machines isn't simple. Electronics must be shielded, motors must resist corrosion. Communication is slow, because radio waves don't travel well underwater. Instead, we rely on acoustic signals, which are much more limited. Every message from a submersible has to fight its way through water that bends, distorts, and swallows sound. The result is that each expedition into the deep is difficult, expensive, and rare. Compare that to space missions. Once a spacecraft escapes gravity, it can travel enormous distances with relative ease, powered by solar panels and inertia. It's not simple, but it's repeatable. The sea doesn't allow that. Each dive is temporary, lasting only as long as the vessel can withstand the pressure and the crew can breathe. It's not an open sky. It's a heavy, suffocating weight, pressing in on all sides. That's why, in a way, space has been easier to study than the ocean depths. Yet despite these obstacles, the deep sea remains one of the most intriguing frontiers. Every glimpse into it reveals something unexpected. Creatures that produce their own light, ecosystems thriving without sunlight, fed instead by chemical energy from vents in the sea floor, vast plains littered with strange formations, trenches deeper than the height of Mount Everest. It's almost as if the planet wanted to remind us that alien worlds don't only exist out there among the stars, they exist right here, beneath our feet, waiting to be noticed. And perhaps that's the most humbling part. For all our talk of progress, of exploration, of pushing boundaries, most of our planet remains hidden to us. That knowledge should make us cautious, but it should also fill us with wonder. The unknown isn't gone, it's closer than we think. So as we begin this long descent together, remember this isn't just a story about the sea. It's a reminder that mystery can exist in the most familiar places. The deep sea holds more secrets than outer space, not because it's larger or more important, but because we've barely looked. And in the spaces we ignore, secrets gather. When we talk about the sea, most of us picture waves breaking on a beach, sunlight glimmering across the surface, maybe a boat cutting through the water on a clear day. That's the ocean most people know, and it feels familiar, even comforting. But that's only the thinnest skin of a world that stretches downward for miles. The surface is not the sea any more than the clouds are the sky. The true ocean lies beneath, layered in zones that grow stranger and more demanding with every metre of descent. To introduce the deep sea is to talk about a hidden world, one that covers most of our planet yet remains almost invisible to us. Scientists divide the ocean into layers, not because they enjoy making neat charts, but because each layer feels like stepping into a different environment altogether. At the top is the epipelagic zone, sometimes called the sunlight zone. It extends from the surface down to about 200 metres. This is the ocean we know, the blue water where fish dart, where coral reefs grow, where photosynthesis happens. It's crowded with life, from the smallest plankton to the largest whales. But below that, the light fades quickly. Slip beyond 200 metres and you're in the mesopelagic zone, often nicknamed the twilight zone. It's not twilight in the poetic sense, but literal. The sunlight dwindles until it's just a dim blue haze. Shapes blur, colours fade, and the world grows ghostly. Here, animals adapt to the fading light by developing enormous eyes to capture what little remains, or by generating their own through bioluminescence. Many creatures in this band spend their days hiding in darkness, then rise toward the surface at night in what's called the Deal vertical migration, the largest animal migration on Earth, happening invisibly every evening as billions of organisms ascend and descend. Descend further, past 1,000 metres, and you enter the Bath pelagic zone, known simply as the midnight zone. By this point, sunlight is gone entirely. It's black, utterly and permanently. The pressure is immense, and the temperature hovers near freezing, yet life persists. Here you'll find anglerfish with their eerie lanterns, gulper eels with oversized mouths, and creatures so translucent they're almost invisible. They don't live here because it's pleasant. They live here because evolution has carved out niches where life can thrive against all odds. Below 4,000 metres is the abyssopelagic zone. The very word abyss suggests what it is: vast, empty, seemingly endless. This is one of the least explored environments on Earth, a place of plains that stretch for thousands of miles, dotted occasionally by seamounts or ridges. Life here is sparse but specialised. Starfish, sea cucumbers, brittle worms, and other creatures manage to survive on the slow rain of organic debris that drifts down from the surface, known as marine snow. Each flake of this snow is the remains of something once alive, microscopic plankton or the leftovers of fish. Over time it settles into a blanket across the seafloor, feeding an ecosystem that would otherwise starve. And deeper still lies the Hadal zone, the realm of trenches and deep-sea canyons that plunge down as far as 11 kilometres. This zone takes its name from Hades, the underworld of Greek mythology, and the comparison is apt. Few places on Earth are as extreme. The Mariana Trench, Challenger Deep, Tonga Trench. These names hint at the scale, but words do little justice to the reality. In these depths, pressure is over 1,000 times what you feel at the surface. Temperatures are just above freezing, and light has no chance of reaching. Yet even here, in what seems like the most hostile corners of our planet, life exists. Microbes cluster around hydrothermal vents. Strange amphipods scurry across the sediment. Scientists have retrieved snailfish from trenches. Fragile creatures adapted to withstand pressures that would flatten most forms of life. Taken together, these layers form a world that feels stacked like hidden floors beneath our feet. We walk the surface, but beneath us stretches an entire vertical wilderness, each band stranger than the last. That's what makes the deep sea so fascinating. It's not one environment, it's many, stacked atop each other, each demanding adaptations from the organisms that call it home. To introduce the deep sea is to reveal not one mystery but many, each tucked into its own zone of light and darkness. Part of what keeps this world hidden is the sheer scale. The ocean covers 70% of Earth's surface, and its average depth is nearly 4 kilometres. If the planet were an apple, the crust of land we live on would be thinner than the skin, and the ocean would be the vast bulk of the fruit. That scale is difficult to imagine, and perhaps that's why most people don't. We glance at maps and see blue areas as though they were blank, but those areas represent mountains taller than Everest, valleys deeper than the Grand Canyon, and plains wider than any desert. It's a landscape larger than all the continents combined, just submerged beneath water. Even if we could strip away the water to reveal the topography beneath, the picture would astonish us. Massive mid-ocean ridges snake across the globe like seams on a baseball. Trenches gouge downward like scars. Seamounts rise like scattered towers. Some of the largest volcanoes on Earth lie underwater, erupting silently in darkness. And still, most of this terrain remains unmapped in detail. For every expedition that returns with new data, dozens more areas remain untouched. We know more about the surface of the Moon, nearly 400,000 kilometres away, than about the ocean floor beneath our feet. That comparison often surprises people. After all, how could we know more about something so far away? The answer lies in the tools. Satellites can scan planetary surfaces from space with radar and optics. Light travels well through space, but water blocks those same signals. To map the ocean, we rely on sonar, which uses sound waves bouncing off the seafloor. It works, but it's slower, less detailed, and harder to cover vast distances. A satellite can map an entire planet in a matter of months. Sonar mapping takes years, and even then it often provides only rough outlines. This is why so much of the deep sea feels like a world apart. It's not only that it's hostile or inaccessible, but that even our best tools struggle against it. Exploration here requires patience, specialised machines, and the willingness to accept that each dive may reveal only a fragment of the whole. And yet every fragment reminds us of just how much we don't know. Consider the creatures that live here. Many of them look like they belong in science fiction. The vampire squid with its cloak-like webbing, the anglerfish with its glowing lure dangling in front of a cavernous mouth, the gulper eel with jaws large enough to swallow prey half its size. These are not exaggerations. They are real animals, shaped by pressures and darkness that have forced evolution into strange directions. Some produce light through chemical reactions, creating blue or green glows in the darkness. Others have bodies so gelatinous they collapse when brought to the surface, unable to survive without the crushing pressure of the depths. Each discovery of such a creature challenges our assumptions about what life can endure. If organisms can survive in trenches miles below the surface, feeding on chemical energy instead of sunlight, then maybe life could exist in places we once thought impossible. This is one reason space agencies like NASA study the deep sea. The conditions resemble those on icy moons like Europa or Enceladus, where oceans lie beneath thick ice crusts. If life can thrive without sunlight here on Earth, it could exist in similar environments elsewhere in the solar system. In that sense, the deep sea is not only a world beneath worlds, it's a model for alien oceans. But even setting aside the parallels to space, the ocean depths are remarkable in their own right. Think of hydrothermal vents, cracks in the seafloor where seawater seeps in, heats up by contact with magma, and then bursts back out, loaded with minerals. Around these vents, entire ecosystems flourish in total darkness, fueled not by photosynthesis, but by chemosynthesis, a process where bacteria convert chemicals into energy. Shrimp, crabs and tube worms cluster around these vents in abundance. It's life thriving where by all logic it shouldn't. And it was discovered only in the late 20th century. That alone shows how new this field of study still is. The more you introduce yourself to the deep sea, the more you realise how much remains hidden. Every expedition seems to return with a new species, a new geological feature, or a new phenomenon. We've found fish that can withstand near freezing temperatures, jellyfish with displays of light more elaborate than fireworks, and microbial life living in rocks hundreds of meters beneath the seafloor. The boundaries of what we consider habitable continue to expand downward. This constant stream of discovery explains why scientists often say the deep sea holds more secrets than outer space. Space exploration is filled with wonder, yes, but space is largely empty. Stars and planets are separated by vast distances. Discoveries there are rare, often taking years of mission planning. The deep sea, by contrast, is crowded with life, activity and change, but almost none of it has been documented. It's not just that it's unknown, it's that it's unknown and full. That combination makes it endlessly compelling. When you look at the ocean on a globe, the irony is obvious. Most of Earth is covered by this vast blue, yet our knowledge of it is shallow. The continents where we live are the exceptions. The ocean is the rule. Introducing the deep sea is less about presenting a single environment and more about reminding ourselves that most of our planet is ocean, most of that ocean is deep, and most of that deep is unexplored. We live on land, but the planet is truly a water world. This perspective changes how we think about Earth. Instead of a planet with oceans, it becomes an ocean with land. And within that ocean are layers stacked like hidden worlds, each more mysterious than the last. The surface is what we see, but beneath lies a continuum of darkness, pressure and life that we've barely touched. To know it fully may take centuries, but to begin knowing it is to remember that mystery still thrives on Earth. When people think of space, they often imagine blackness stretching forever, a silence so complete it feels heavy, and scattered points of light marking distant suns. It's easy to forget that those same qualities exist right here on Earth if you go far enough beneath the waves. The ocean, in many ways, is a mirror to the cosmos, both a vast, dark, and seemingly infinite to our senses. Both conceal wonders that strain the limits of imagination, and both remind us that humans are small, fragile creatures surrounded by environments we can barely comprehend. Standing at the shore, staring out across the water, the sea does to our eyes what the night sky does. It stretches beyond sight, giving the impression of endlessness. No matter how far you look, the horizon hides what lies beyond. In the same way, no matter how far into the stars you gaze, distance keeps secrets just out of reach. That resemblance between the sea and space has shaped human imagination for centuries. Sailors once compared long voyages across oceans to journeys through the heavens. Writers still use the metaphor of the sea to describe space travel, calling spacecraft ships and speaking of cosmic oceans. The resemblance is more than poetic, it's structural. The ocean is not empty. It is filled with water, of course, but also with life, minerals, mountains, and currents. Space is not empty either. It contains dust, gas, radiation, planets, stars, and galaxies. Both are vast frontiers, and both give us the sense of peering into a domain that is indifferent to us. The ocean doesn't care whether we enter it, and space doesn't either. In both cases, survival requires careful preparation and technology. Our bodies weren't made for either realm. We need machines to breathe, to shield us, to move us forward. A diving suit and a spacesuit are cousins in design, both meant to protect a fragile body from crushing pressures or suffocating voids. That's why, when engineers design deep-sea submersibles, they often look to spacecraft for inspiration, and vice versa. Another similarity lies in how we study them. In space, telescopes act as our eyes, gathering light from distances we can't travel. In the sea, sonar acts as our ears, bouncing sound through darkness where light cannot reach. Both methods create maps of the unseen, turning the invisible into something we can picture. Neither shows us reality directly. Telescopes reveal ancient light, snapshots of stars as they were long ago. Sonar reveals outlines, shadows shaped by sound waves. Both leave room for interpretation, and both remind us that our knowledge is indirect. We do not walk into space or stroll across the seafloor. We piece together glimpses and models. There's also the psychological similarity. People describe feeling awe when gazing at the stars, a sense of being small within something immeasurably vast. That same feeling arrives when descending into the deep or even imagining it. Knowing that miles of water stretch above you, with pressure enough to crush metal, brings a recognition of scale. The human brain isn't good at imagining extremes, whether infinite space or crushing pressure, but both trigger the same recognition. We are temporary beings in a universe that dwarfs us. That recognition can be terrifying, but it can also be comforting. It puts worries into perspective. A missed appointment or a stressful day feels smaller when you consider the immensity of oceans or galaxies. The connection between the sea and the cosmos isn't just emotional. Scientists use the deep ocean as an analogue for space exploration. Consider the hydrothermal vents discovered in the late 20th century. Here, in the absence of sunlight, entire ecosystems thrive on chemical energy. That discovery changed biology. Before, we believed sunlight was essential for life. Afterward, we realized that life could thrive in conditions we once thought impossible. Suddenly, the possibility of life existing in extraterrestrial oceans beneath the ice of Europa or Enceladus seemed far more likely. The events of Earth became blueprints for alien biology. By studying them, we aren't just learning about our oceans, we're rehearsing for discoveries beyond Earth. This is why agencies like NASA and ESA often collaborate with oceanographers. A robotic submersible exploring a trench is similar to one that might one day explore Europa's ocean. The engineering challenges overlap: how to withstand pressure, how to navigate without light, how to send data back through hostile environments. A probe under ice is not so different from a probe under miles of water. Each dive into the deep sea becomes practice for missions yet to come. And then there's the way both realms hold their mysteries not in abundance, but in silence. Space hides its secrets in distance. The ocean hides them in depth. Both remind us that visibility is not the same as knowledge. We can look up at stars every night and still not know what lies between them. We can look at the sea every day and still not know what lies beneath its surface. Visibility gives us the illusion of understanding, but the truth is always deeper, always harder to reach. There's also something fascinating in how both realms bend time. In space, we see stars as they were millions of years ago because light takes time to travel. In the sea, we see ecosystems that have existed with little change for millions of years, sheltered in darkness. Both are time capsules. The night sky shows us the past of the universe, while the deep sea preserves the past of Earth. Strange fish, archaic crustaceans, even microbes around vents may represent ancient branches of life, untouched by surface changes. It's as though space shows us cosmic history, and the ocean shows us biological history, each a record written in different languages. Another reflection between them is how they shape myth. Ancient cultures looked up at constellations and told stories of gods and heroes. They looked at the sea and told stories of monsters and realms beneath. Both served as canvases for imagination. Today, science has replaced much of that mythology with data, but the sense of mystery lingers. People still talk of aliens with the same mixture of fear and wonder as they once spoke of sea serpents. And the deep sea still produces creatures so strange they might as well be extraterrestrial. When the first photographs of giant squid were released, they seemed like beings from another world. In a sense, they are. From the other world that exists just below our own. The way humans approach both realms is also similar. We send machines first: satellites, probes, telescopes, submersibles, ROVs, sonar. Machines extend our senses into places our bodies can't survive. Later, sometimes we send people, astronauts to orbit, aquanauts in submersibles, but even then their reach is limited. We never stay long. We dip into the environment, gather what we can, and retreat. These are not places we inhabit, but places we visit briefly. The difference is that space holds the possibility of colonization, while the deep sea does not. No one dreams of cities on the ocean floor the way they dream of colonies on Mars. The sea is too hostile, too heavy. It is a place to study, not to settle. And yet the sea and space remain linked in another way. Both remind us of our dependence. Space surrounds Earth, holding the sun that powers our lives. The sea surrounds continents, regulating climate, producing oxygen, and feeding billions. Without either, we wouldn't exist. One gives us energy from above, the other from below. Both sustain us while hiding most of their workings. That's another reason the sea feels like a mirror to the cosmos. Both are vital, and both remind us how little control we have. When you look at Earth from space, what stands out isn't land but ocean. The planet is blue because of water. Astronauts often describe the sight as overwhelming. From orbit, the Earth looks like a fragile marble floating in blackness, wrapped in swirls of white clouds and dominated by the blue of oceans. That image collapses the distinction between sea and space. The two are part of the same whole, a planet adrift in a larger ocean of stars. This is why introducing the deep sea often feels like introducing a twin to space. Both share qualities that make them humbling, frightening, and beautiful all at once. Both demand technology, patience, and courage to explore. Both test the limits of imagination. And both, when studied closely, tell us something about ourselves. We are creatures drawn to the edge of what we know. Whether that edge is above us in the night sky or beneath us in the abyss, the pull is the same. The sea as a mirror to the cosmos isn't only metaphorical, it's practical, scientific, emotional, and cultural. When we study one, we often learn about the other. When we imagine one, we use the language of the other. And when we reflect on our place in either, we find the same answer. Small, temporary, yet endlessly curious. And so, while telescopes look outward and submersibles look downward, both are part of the same human impulse. The need to know what lies beyond the horizon, whether that horizon is the edge of the atmosphere or the edge of the continental shelf. The unknown calls, and in both sea and sky, the echoes sound remarkably alike. It feels counterintuitive to say we know more about Mars than the Mariana Trench. After all, one is a barren planet millions of kilometres away and the other lies right here on Earth. A trench we could in theory reach in a matter of hours if we boarded the right vessel. And yet, the comparison is true. Our maps of Mars are detailed, showing valleys, ridges and mountains with clarity down to meters. The Mariana Trench, despite being the deepest natural feature on our planet, remains poorly understood. The irony is sharp. How is it that we've mapped and studied a distant planet more thoroughly than we have our own ocean floor? Part of the answer lies in the simple difference between looking outward and looking downward. Space, as vast as it is, offers us transparency. Light travels freely in a vacuum. Telescopes gather that light and send back images. Satellites orbit Mars and beam down maps created from radar and cameras. In contrast, the ocean is opaque to light. Just a few hundred meters below the surface, sunlight disappears. Beyond that, even the most advanced cameras see only what artificial lights can illuminate, which usually isn't much. Entire mountains and valleys remain invisible because light cannot reach them. If you want to know what lies beneath, you need different tools, and those tools are slower, harder to use, and more expensive. That's where sonar comes in. Instead of light, sonar uses sound. Ships send out sound pulses that travel downward until they strike the seafloor and bounce back. By measuring how long it takes for the echo to return, scientists can estimate the depth and create a rough map. But sonar isn't precise everywhere. Its resolution depends on how close the ship is to the area being mapped, and given that oceans cover more than 70% of the planet, scanning it all with precision would take centuries. The result is that much of the ocean floor has been mapped only in broad strokes, enough to show major features like ridges or trenches, but not enough to reveal details. By contrast, orbiters around Mars have scanned the entire surface systematically, unhindered by water. That's why we can talk about craters on Mars with more certainty than we can about features of the Mariana Trench. Another reason lies in funding and focus. Space exploration captures imagination. It represents the future, the possibility of colonization, and the pursuit of questions about life beyond Earth. Governments and private companies pour billions into space programs. Mars has rovers, orbiters, and plans for human missions because it's a target filled with symbolic meaning. Oceans, on the other hand, lack that same appeal. They are familiar even if their depths are not. They don't carry the same promise of discovery in the public imagination, even though scientifically they may hold far more immediate mysteries. Exploration of the seas has often been left to small groups of scientists underfunded compared to space agencies. And yet, the Mariana Trench represents a frontier every bit as extreme as Mars. At its deepest point, Challenger Deep, the trench reaches nearly 11 kilometers down. To put that in perspective, if Mount Everest were dropped into the trench, its peak would still lie more than a mile below the surface. The pressure there exceeds 1,000 atmospheres, enough to crush most submarines instantly. Only a handful of missions have ever reached those depths. Jacques Piccard and Don Walsh descended in the Trieste in 1960, spending barely 20 minutes on the seafloor. James Cameron returned in 2012, piloting his deep-sea Challenger. Since then, a few more dives have been made with advanced submersibles, but each required enormous preparation, funding, and engineering. By contrast, spacecraft orbit Mars year after year, sending streams of data continuously. Technology also plays a role. Once a satellite is in orbit, it can scan an entire planet with relative efficiency. Submersibles, however, must endure crushing pressure and corrosive saltwater, while carrying enough power to sustain instruments and, in some cases, human passengers. Communication is limited too. Radio waves travel easily in space, but in water they quickly fade. Submarines communicate primarily through acoustic signals, which are slow and often unreliable. That makes real-time exploration difficult. Rovers on Mars can be controlled remotely with instructions sent across millions of kilometers. Submersibles in the Mariana Trench must often operate with limited guidance, recording data that can only be reviewed later. There's also a cultural element. Space exploration fits a narrative of progress and expansion. It's about reaching new worlds, planting flags, and dreaming of civilizations beyond Earth. Ocean exploration, by contrast, feels like turning inward, into darkness. It's harder to frame as a grand adventure. There are no alien civilizations waiting in the trench, no promise of terraforming or colonization. What waits there are microbes, strange fish, and geological formations. To a scientist, these are extraordinary, reshaping our understanding of life and Earth itself. To the broader public, they may not seem as exciting as the idea of walking on Mars. And so, resources follow interest, and interest drifts upward rather than downward. The irony is that what lies in the deep sea may actually matter more to our immediate future. The ocean regulates climate, stores carbon, and provides food for billions. Understanding how it works at every level, including the deepest trenches, may be vital for managing Earth's future. Hydrothermal vents, discovered only a few decades ago, revealed entire ecosystems based on chemical energy. Studying them expanded biology in directions no one expected. Who knows what else waits in the trenches? Perhaps new organisms with adaptations that could inspire medicine or technology. Perhaps geological processes that help explain earthquakes or tsunamis. The Mariana Trench is not just a curiosity, it's a key to understanding our planet. And still, Mars wins the spotlight. It's worth remembering that exploration is not purely logical. It's emotional, political, and cultural. We choose to study Mars because it captures imagination, not because it's easier to reach. The fact that it has been easier to map Mars than the trench says more about priorities than about possibility. If we devoted the same energy to ocean exploration, we could know far more than we do now. But even with limited missions, what little we've learned from the trench is extraordinary. At depths once thought uninhabitable, scientists have found life. Amphipods, snailfish, microbial mats, all thriving in pressure and darkness. Some of these organisms feed on material drifting from above. Others rely on chemosynthesis, using chemicals seeping from rocks. Their very existence expands our definition of where life can survive. That's why studying the trench is so valuable. Every new discovery suggests that life elsewhere in the universe may be more likely than we once believed. If organisms can endure the trench, perhaps they can endure alien oceans beneath the ice of Europa or Titan. In that sense, the Mariana Trench doesn't compete with Mars. It complements it. Each reveals something about the other. It's also worth remembering that our relationship to the trench is recent. For most of history, no one even knew it existed. Depth was a vague concept measured by lowering weighted ropes overboard, and those ropes rarely reached more than a few kilometres. It wasn't until the 20th century with sonar and deep-sea submersibles that we began to glimpse the true scale. Compare that to space, where telescopes have shown us planets for centuries. The trench is not only hidden by water, but by history. We simply haven't had the tools long enough to know it as well as we know Mars. And yet, even now, we find ourselves facing the same truth. To map the trench completely would require dedicated missions year after year, with the kind of funding usually reserved for space. Until that happens, Mars will remain better known. The irony of standing on a planet and knowing more about a neighbour world than about our own depths should make us pause. It suggests that the greatest frontier isn't always the one farthest away. Sometimes it's the one right beneath us, hidden not by distance but by difficulty. The Mariana Trench is a reminder that mystery thrives where we don't look. Mars has been the focus of generations, so we know it well. The trench has been largely ignored, so it keeps its secrets. And that's perhaps the best answer to why we know more about Mars than the trench. Because attention directs knowledge. Where curiosity points, discovery follows. Where it does not, mystery remains. When we talk about the deep sea, we often focus on the darkness, the way sunlight fades until it disappears completely. But what really defines that world isn't just the absence of light, it's the presence of pressure. Darkness may hide, but pressure rules. The deeper you go, the more relentless it becomes. A weight so immense it reshapes everything that tries to live there, and challenges everything we build to explore it. At the surface, where we stand and breathe without thinking, pressure is already present. The air above us presses down with the weight of the atmosphere. We don't feel it because our bodies are adapted to it, our lungs and blood and tissues perfectly balanced against it. But step into the ocean, and that pressure multiplies. For every 10 meters you descend, you add another atmosphere of pressure. At 100 meters, that's 10 times the pressure you feel on land. At 1,000, it's 100 times. By the time you reach the deepest trenches, it's over 1,000 times greater. Imagine the weight of 50 jumbo jets pressing down on every square meter of your body. That's what pressure means in the deep sea. To understand how extreme this is, consider the Mariana Trench again. At Challenger Deep, nearly 11 kilometers down, the pressure reaches about 1,100 atmospheres. That's 16,000 pounds per square inch. A steel hull the thickness of a car door would collapse instantly. Submersibles built for these depths use spherical designs because a sphere distributes stress evenly, and even then the walls must be many inches thick, made of titanium or specialized alloys. Windows, when they exist, are tiny portholes made from acrylic so strong it looks more like stone than glass. Every descent is a battle against crushing force. For humans, the limits come quickly. Divers can descend safely with specialized equipment to a few hundred meters, but beyond that, the risks rise exponentially. At around 300 meters, even with mixed gases like helium and oxygen, the body begins to suffer from nitrogen narcosis and oxygen toxicity. The longest human dives, using saturation diving techniques, rarely go beyond 1,000 feet. That's about 300 meters, a fraction of the ocean's total depth. Beyond that, machines must take over, and yet life exists there. Organisms have evolved to withstand pressures that would turn most creatures into pulp. Some fish found in the trenches have bodies with no air-filled cavities, no swim bladders that could collapse. Their tissues contain proteins that stabilize cell structures against the crushing weight. Their enzymes are adapted to function in conditions where normal proteins would fold and fail. Microbes discovered in deep trenches thrive in pressures 100 times greater than what humans experience at the surface, and when scientists bring them up to normal pressure, they often die. For them, what we consider crushing is normal. This is perhaps the most humbling part of pressure in the deep sea. It redefines normal. What feels impossible to us is everyday reality for the creatures that live there. Anglerfish don't struggle against the weight. Snailfish don't collapse under it. They're shaped by it, built to thrive where we would be destroyed. It's a reminder that life adapts not to what's comfortable, but to what exists. And pressure, as unforgiving as it is, provides niches where evolution has carved out survivors. The challenge for us comes when we try to join them. Technology has to compensate for what our bodies cannot endure. Early submersibles often failed under pressure. Hulls buckled, seals burst, equipment cracked. Each failure taught engineers how to design better vessels, but the margin for error remains thin. When James Cameron descended to the Challenger Deep, his submersible was a vertical torpedo with walls nearly 3 inches thick. Even then, the pressure squeezed it slightly, as though the sea were testing its resolve. For the pilot inside, every groan of metal carried a reminder of where they were, a place where survival depended entirely on engineering. Pressure also explains why exploration is so rare. Each dive to the deepest parts requires enormous resources. A single flaw, a tiny imperfection in the hull could be catastrophic. Unlike in space, where a leak might be patched temporarily, pressure underwater is instantaneous. There is no time for repair. Collapse happens faster than recognition. That's why missions are few and far between. It's not lack of interest alone, but the sheer danger and difficulty posed by pressure. Yet pressure isn't just a barrier. It shapes the very geology of the planet. Trenches exist where tectonic plates collide, one sliding beneath another. The immense forces involved create earthquakes, tsunamis, and volcanic activity. Pressure in these regions doesn't just affect biology, but geology itself. Hydrothermal vents, for example, form because seawater forced deep into the crust under pressure, heats up, and then erupts back into the ocean. Without pressure, those vents wouldn't exist, and without them, the unique ecosystems around them wouldn't either. Pressure is the hidden architect of life in the deep. For scientists, studying organisms that survive such extremes offers insights far beyond curiosity. Proteins that resist pressure could inspire new medicines. Enzymes that function in crushing depths could be used in industry. Even understanding how cell membranes stay intact under immense force could lead to breakthroughs in biotechnology. The adaptations of deep-sea life show us not just the limits of biology, but the possibilities of resilience. Pressure also changes how sound travels. In the deep ocean, sound can move farther and faster than at the surface. Whales use this property to communicate across entire ocean basins. Submarines rely on it for stealth and detection. Pressure shapes the very physics of the ocean, turning it into a medium where light disappears but sound becomes dominant. That's another way the deep mirrors space. In space, light carries our knowledge. In the sea, sound does. And pressure determines the rules for both. The weight of darkness, then, is not just poetic. It's literal, measurable, and relentless. To introduce the deep sea without acknowledging pressure would be like describing space without mentioning vacuum. It defines the environment at every level. And yet, just as astronauts learn to navigate vacuum, oceanographers and engineers learn to navigate pressure. Each dive is a step into a realm where survival is precarious, but each dive also expands our understanding of what life and technology can endure. it's worth remembering that pressure is not inherently hostile. It is simply there. To creatures adapted to it, the deep is no more crushing than the surface is to us. The challenge lies in crossing boundaries. Humans are creatures of one atmosphere. We struggle when moving beyond it. Fish of the trench are creatures of 1,000 atmospheres. They struggle when brought above it. Each form of life has its own balance, its own normal, and pressure enforces those boundaries. What seems unimaginable to us is simply ordinary to them, and so the weight of darkness becomes both barrier and teacher. It keeps secrets safe, preserving environments we've barely glimpsed. It reminds us that survival depends on adaptation, and it challenges us to keep building, testing, and learning, not because we will ever live in those depths, but because understanding them teaches us more about the resilience of life and the power of the planet itself. When sunlight fades and disappears beyond the reach of even the clearest waters, you might assume life would vanish too. For a long time, scientists believed that very thing. They thought the deep sea would be a barren desert, too dark and too cold to support anything more than the occasional drifting particle or a handful of microbes. But the truth turned out to be far stranger and far richer. In the absence of light, life hasn't vanished. It has reinvented itself. The creatures of the deep are not pale shadows of surface species. They are their own forms entirely, evolved to thrive in conditions that seem impossible. They are creatures born of night, sculpted by an environment without sunlight. The first thing to understand is that without light, photosynthesis cannot exist. Plants, algae, and phytoplankton, which form the base of most food chains in the upper ocean, cannot survive here. Instead, life relies on different strategies. One of the most common is scavenging. Organic matter from the surface, dead fish, plankton, even entire whales, eventually sinks into the depths as what scientists call marine snow. To us, it's an eerie term. To the creatures below, it's sustenance. Tiny flakes drift slowly down, and the organisms of the deep make do with what arrives. For some, that's enough. For others, survival depends on innovations far stranger. Bioluminescence is one of those innovations. In a world without sunlight, light becomes a tool. Many deep-sea creatures produce their own glow through chemical reactions inside their bodies. Some use it to lure prey. The anglerfish is perhaps the most famous, with its dangling lure that shines in the darkness, attracting unsuspecting fish into its waiting mouth. Others use light to confuse predators, releasing clouds of glowing fluid that act like underwater smoke bombs. Still others use it for communication, flashing signals to attract mates, or to signal their presence to others of their species. It is estimated that more than 3/4 of deep-sea organisms produce some form of light. The ocean depths, far from being lifeless, are full of sparks and glimmers, like stars scattered across a night sky. The shapes of these creatures can be startling. Freed from the need to blend with sunlit waters, many have evolved features that seem almost alien. Some are nearly transparent, their organs visible through gelatinous skin. Others are jet black, absorbing what little light exists. Eyes can be enormous, adapted to detect the faintest glimmers, or they can be absent entirely, replaced by other senses. Mouths often seem oversized compared to body size, a reflection of scarcity. In a place where food is rare, no opportunity can be wasted. If a fish encounters prey, it needs to swallow it whole, regardless of size. That's why you see creatures like the gulper eel, capable of expanding its jaw to swallow animals nearly as large as itself. One of the most surprising discoveries came with hydrothermal vents. In the late 1970s, scientists exploring the Galapagos Rift found hot springs on the seafloor, spewing mineral-rich water heated by volcanic activity. Around these vents clustered entire ecosystems, giant tube worms, clams, crabs and shrimp, all living without sunlight. Their food chain was based not on photosynthesis, but on chemosynthesis. the process of bacteria converting chemicals like hydrogen sulfide into energy. This discovery shocked biologists. Until then, the assumption had been that sunlight was the foundation of all ecosystems. Suddenly, here was proof that life could exist entirely without it, thriving in conditions of darkness, heat, and pressure. These vent communities are not small curiosities. They represent a whole new way for life to organise itself. Tube worms, for example, grow to over 2 meters long and lack mouths or digestive systems. Instead, they house bacteria inside their bodies that perform chemosynthesis, trading a safe home for energy. Shrimp and crabs graze on microbial mats, forming complex food webs. Even here, predators exist, adapted to hunt among the vents. And these ecosystems, independent of the sun, suggest that life elsewhere in the universe might not need sunlight either. If bacteria can thrive on chemical energy in Earth's depths, perhaps they can do the same in subsurface oceans on Europa or Enceladus. But it's not only around vents that life flourishes. Across the abyssal plains, starfish, brittle stars, sea cucumbers, and countless smaller organisms crawl slowly, feeding on the steady drizzle of marine snow. Some species cluster around whale falls, the remains of whales that sink after death. These carcasses create oases of life, sustaining entire communities for decades. First come scavengers that strip away the flesh. Then come organisms that feed on the bones, aided by bacteria that break down lipids. Over time, the whale's body becomes a miniature ecosystem, a reminder that even in the deep sea, death creates new beginnings. The adaptations of deep-sea creatures go beyond feeding strategies. Many have metabolisms tuned to extreme scarcity, allowing them to survive long periods without food. Some can slow their activity almost to dormancy, conserving energy until opportunity arises. Others reproduce in unusual ways, ensuring survival despite isolation. The anglerfish, again, is an example. In some species, males are tiny compared to females. When a male finds a female, he bites into her skin and fuses with her body, becoming little more than a permanent source of sperm. It may sound grotesque, but in an environment where encounters are rare, it ensures reproduction. Evolution, in the deep sea, is pragmatic. The diversity of forms also speaks to how little we've seen. Every expedition to the depths brings new species. Some are small, new worms, crustaceans, or jellyfish. Others are startling, fish with transparent heads, squid with improbably long arms, jellyfish with displays of light unlike anything seen at the surface. Each discovery reminds us that our imagination struggles to match reality. Science fiction often invents alien beings, yet Earth already holds creatures more bizarre than most fiction. The deep sea, in that sense, is the universe's preview of what creativity looks like when shaped by pressure and darkness. Life without sunlight also challenges our assumptions about habitability. For centuries, humans equated life with light, equating the sun with vitality. Agriculture, photosynthesis, warmth, all tied to the star above us. Yet in the deep sea, life proves otherwise. It thrives without sun, without warmth, without seasons. It relies on chemistry, patience, and resilience. This realization expands the scope of what we consider possible. If Earth can support such life, why not other worlds? The deep sea is not just a hidden ecosystem. It's a lesson in humility. It's also a lesson in interconnectedness. Though deep-sea creatures live far below, they are linked to the surface. The marine snow that feeds them originates in sunlit waters. The carcasses that fall to the depths come from animals that lived closer to the surface. Even vent communities, seemingly independent, rely on minerals and energy driven by tectonic activity. The deep sea is isolated yet connected, a reminder that ecosystems on Earth, no matter how distant, are never truly separate. For humans, the challenge remains how to study these creatures without destroying them. Many deep-sea organisms cannot survive being brought to the surface. Their bodies collapse without pressure, their proteins denature, their membranes fail. Scientists have developed pressurized containers to keep them alive for study, but even then, survival rates are low. Much of what we know comes from fleeting glimpses, video footage captured by remotely operated vehicles. That makes every expedition precious. Every image of a glowing squid or a strange jelly is a rare window into a world that usually remains invisible. And yet, even these brief glimpses reveal an extraordinary truth. Life adapts endlessly. Darkness and pressure may seem like insurmountable barriers, but life reshapes itself to fit. It glows, it stretches, it fuses, it scavenges. It becomes transparent or black, small or enormous, simple or intricate. Each adaptation is a story of persistence. Creatures born of night remind us that survival isn't about comfort, but about possibility. And in the ocean depths, possibility takes forms stranger than we could have imagined. Somewhere between the brightness of the surface and the blackness of the abyss lies a band of ocean that is neither one nor the other. It isn't illuminated enough for plants to grow, but it isn't yet dark enough to feel like the bottomless void below. This is the region scientists call the mesopelagic, though to most people it's simply known as the twilight zone. It begins around 200 meters beneath the surface and stretches to about 1,000. To enter it is to witness a slow unravelling of light, a place where colours fade away and shadows begin to dominate. It is in many ways the ocean's in-between world. At first glance, the twilight zone seems empty. Sunlight weakens quickly here, filtering down in faint bluish beams that struggle to reach any distance. Red, orange and yellow vanish within the first 100 meters, absorbed by water. By the time you sink into this band, everything is tinged in shades of blue and green. If a diver in a red suit descended to these depths, that suit would look black. Colours we take for granted at the surface lose their meaning here. For many creatures, this fading of colour is an opportunity. Being red in the twilight zone makes an animal effectively invisible, hidden in a world where red light no longer exists. That's why so many deep-sea fish are a dull crimson shade. They're not trying to stand out, they're trying to disappear. But the twilight zone is far from empty. In fact, it may hold more fish by weight than all the rest of the ocean combined. Tiny lanternfish, bristlемouths, and other small species gather here in staggering numbers, forming what sonar operators once thought was the ocean floor itself. When early sonar reading showed a false bottom hundreds of meters down, scientists were confused. The floor seemed to rise and fall every day, vanishing at night and sinking again in the morning. Eventually, they realized it wasn't the seafloor at all, but an immense layer of living creatures, migrating daily in the largest movement of biomass on the planet. Billions of fish and invertebrates ascend at night to feed in the surface waters, then descend at dawn to hide in the safety of the twilight. This daily migration dwarfs anything seen on land. Herds of wildebeest, flocks of birds, none compare to the scale of what happens silently in the sea every day. Life here is defined by compromise. Light is scarce but not absent. Predators adapt with enormous eyes, tuned to capture the faintest glimmers. Some, like the hatchetfish, have upward-facing eyes that scan for the silhouettes of prey, outlined against the dim surface glow. To avoid being seen themselves, many species use counter-illumination. Their undersides glow with bioluminescent light that matches the faint brightness from above, erasing their shadows and making them invisible from below. It's camouflage perfected not with colour but with light itself. The twilight zone is also a place of trade-offs in energy. Food is limited, so many creatures are small, conserving energy by keeping their bodies simple. Lanternfish, though tiny, exist in such numbers that they may be the most abundant vertebrates on Earth. Bristlemouths, with their needle-like teeth, may outnumber all other fish species combined. These little fish, barely noticed at the surface, form the base of a food web that sustains larger predators and even influences global carbon cycles. When they migrate daily, they carry carbon from the surface into the depths, effectively pumping it downward. In this way, the twilight zone plays a role in regulating Earth climate, even though most people have never heard of it. Predators here include squid, larger fish, and sometimes visitors from above: tuna, swordfish, sharks, all capable of diving deep to hunt before returning to brighter waters. Many of them rely on speed, seizing prey before it can vanish into the shadows. Others rely on stealth, blending into the faint blue light until the last moment. The diversity of strategies mirrors the diversity of forms, each adapted to a world balanced between visibility and concealment. The creatures of this region often appear strange to human eyes. Take the hatchet fish, with its laterally flattened body and reflective scales that glitter like metal, designed to reflect surrounding light and disappear against the background. Or the dragonfish, with needle-like teeth and a lure under its chin, glowing faintly to attract prey. Unlike most bioluminescent animals, dragonfish produce red light, invisible to most other species. With this ability, they gain a secret advantage, seeing prey illuminated in a wavelength others cannot detect. It's as if they've evolved their own private flashlight, invisible to the rest of the community. And then there's the squid. Many species of squid thrive in the twilight zone, some with light-producing organs, others with long arms and jet propulsion built for ambush. They are both prey and predator, caught in the endless cycle of survival that defines this band of ocean. In some places, swarms of small squid gather in such numbers that they attract whales, which dive deep to feast on them. A sperm whale can dive more than 1,000 meters to hunt in these depths, staying submerged for over an hour. Their battles with giant squid, legendary in human imagination, play out here in the twilight and beyond, rarely witnessed but leaving scars on the whales' bodies as proof. The twilight zone also highlights how little we know. Because it lies beyond the reach of casual diving and beneath the comfort of surface exploration, it is rarely studied compared to other regions. Yet the more we learn, the more significant it appears. Fisheries have begun targeting lanternfish and other twilight species, seeing them as an untapped resource. But scientists warn that these creatures play vital roles in Earth systems. Remove them, and you could disrupt carbon cycles, climate regulation, and predator-prey dynamics across the ocean. In other words, the twilight zone may be invisible, but it is essential. Studying it is difficult. Traditional nets often destroy fragile animals or fail to capture them at all. Cameras struggle in the low light, and artificial lights can alter animal behavior. Recently, scientists have developed quieter, less intrusive tools, special cameras that can operate in near darkness, gentle nets that preserve delicate bodies, and acoustic systems that track migrations. Even so, each expedition returns with surprises. New species appear regularly. Patterns of behavior emerge that no one expected. It is a reminder that the twilight zone is not simply a curiosity, but a living engine of the planet, hidden in half-light. There's something fitting about calling it the twilight. Twilight is a time of change, of transition. On land, it's the brief hour between day and night. In the sea, it's a permanent state, a place defined by what it lacks as much as what it has. It lacks full light, but not all light. It lacks abundant food, but not all food. It lacks absolute darkness, but not full visibility. It is in essence the middle child of the ocean, often overlooked, but holding enormous influence. The creatures born here show us how adaptable life can be when the rules shift. They master camouflage not by blending into rocks or plants, but by bending light itself. They migrate daily in numbers so vast they alter the chemistry of the planet. They thrive in scarcity, finding ways to make survival possible where conditions seem marginal. If the deep abyss represents the extreme of survival without sunlight, the twilight zone represents survival with just enough light to shape but not sustain life. It's a balance, and life has learned to walk that line with astonishing creativity. When scientists describe the twilight zone, they sometimes compare it to a frontier we are only beginning to glimpse. Unlike the abyss, where exploration is rare and fleeting, the twilight is close enough to study regularly, but distant enough to resist easy understanding. It is accessible but mysterious, a vast middle world that reminds us how much remains unseen even just a few hundred meters below the surface, and perhaps that's why it captures imagination. It's not the farthest or the darkest, but it is the place where light and shadow wrestle, where colour fades away, and where life invents new ways to survive in between. To picture it is to imagine a world of endless dusk, where the sun never quite rises and never fully sets, where animals glow with their own lights, and silhouettes drift in blue-green haze. It is a realm we rarely notice, but one that sustains the oceans, regulates the earth, and holds mysteries as profound as any galaxy. In this sense, the Twilight Zone is not just a layer of the sea, it is a reminder that transition itself can be a place of wonder. If you could descend past the twilight, through the midnight zone where darkness becomes complete, eventually you would reach a region that is unlike anything above it. The ocean floor at these depths stretches outward in vast, flat expanses called abyssal plains. They cover more than half of Earth's surface, making them one of the largest environments on the planet, yet they are almost never thought of. Few people even know they exist, hidden beneath kilometers of water, silent and seemingly empty. They are deserts of the deep ocean, as endless and as stark as space itself. The abyssal plains begin around 4,000 meters below the surface and extend down to about 6,000. At this depth, there is no sunlight at all. Temperatures hover just above freezing. The pressure is immense, hundreds of times greater than at the surface, enough to crush most machines if they were not built for it. To stand on the seafloor here, even inside a submersible, is to stand in a world as alien as any planet we have yet explored. And yet, this alien world is Earth's most common environment, larger than all land habitats combined. The first impression of the abyss is emptiness. The plains are mostly flat, shaped by sediments that drift down over millions of years, creating a smooth sea floor broken only by occasional ridges, trenches or seamounts. It is not a landscape of dramatic variety, but of vast uniformity, stretching further than the eye can see. To explorers, it can feel like standing in a desert where sand stretches endlessly in every direction. Only here the sand is fine sediment, the remains of countless microscopic organisms that once floated in surface waters. This slow rain of organic material, called marine snow, is what sustains life here. Each flake is a particle of dust, a fragment of a body, a piece of carbon drifting down through darkness until it settles on the plains. Despite the bleakness, life does exist here, though it is sparse and spread thinly. Sea cucumbers crawl slowly across the sediment, feeding by sifting through it. Starfish, brittle stars and worms burrow into the soft floor searching for nutrition. Some deep-sea fish patrol the emptiness, their bodies adapted to low energy and long waits between meals. In many ways, survival here resembles survival in a desert. Food is rare, so every organism must make the most of what little arrives. Movements are slow, metabolisms are reduced, and competition is minimized simply because few creatures can endure the conditions. One of the remarkable things about abyssal life is how patient it is. Organisms here may go days or even weeks without food. They rely on slow metabolisms, efficient digestion, and the ability to extract every bit of energy from what little they consume. Some bury themselves in sediment to wait, conserving energy until something edible drifts within reach. Others roam in search of carcasses, dead fish, squid, or in rare cases the massive bodies of whales that sink to the bottom. These whale falls become oases of life in the desert, attracting scavengers from miles around. First come the large predators, tearing into the flesh. Then smaller creatures arrive to strip away what remains. Finally, bacteria take over, breaking down bones and lipids, sustaining communities for decades. Each whale fall is like a forest sprouting suddenly in the desert, flourishing for years before fading again into emptiness. Although abyssal plains may seem monotonous, they are shaped by geology in subtle ways. Mid-ocean ridges where tectonic plates spread apart cut across the plains. Seamounts rise like mountains from the sediment, sometimes reaching high enough to influence ocean currents. Trenches and fracture zones add variety, though they are less common than the endless flats. In some places, volcanic activity adds warmth and minerals, creating isolated hotspots of life. These features remind us that the abyss is not entirely still, even if its movements occur on geological timescales. For scientists, studying the abyss is both frustrating and fascinating. The vastness makes exploration difficult. Remote-operated vehicles can capture video, but they cover only tiny areas compared to the immensity of the plains. Sampling sediment provides clues about life and chemistry, but again, it is a fragment of a larger whole. It's like trying to understand a desert by studying a single grain of sand. Yet even from these fragments, extraordinary insights emerge. Microbes have been found deep in the sediments, surviving without sunlight for millions of years. Some of these microbes metabolize slowly enough that their lifespans may stretch for centuries. They remind us that even in apparent stillness, life finds a way. The abyssal plains also play a role in Earth's carbon cycle. When carbon-rich material sinks from the surface and settles in sediments, it can remain buried for thousands of years. This process, known as carbon sequestration, helps regulate the planet's climate. Without it, more carbon would remain in the atmosphere, warming the planet further. In this sense, the abyss acts as Earth's hidden regulator, quietly balancing conditions for life above. The creatures crawling across the plains may seem insignificant, but collectively, they are part of a planetary system that keeps Earth habitable. Exploration of these plains has also revealed new species, with adaptations unlike anything else. Some worms feed on bones using specialized bacteria. Certain sea cucumbers have transparent bodies that reveal their organs. Other animals use bioluminescence even here, flashing briefly to startle predators or to attract mates. Many are fragile, collapsing when brought to the surface, making them difficult to study. Each expedition returns with surprises, and each surprise reminds us how incomplete our picture remains. What makes the abyss so striking is how it mirrors the emptiness of space. Both are vast, dark and silent. Both give the impression of infinity. In space, stars are scattered across distance. In the abyss, creatures are scattered across emptiness. Both inspire awe, not because of what they contain, but because of how much they lack. Standing on the abyssal plain is like standing in a desert beneath a night sky. Emptiness above mirrored by emptiness below. It is no wonder that scientists and explorers often describe it in cosmic terms. Yet even here, in this apparent desert, life persists. That persistence is a reminder that emptiness is rarely absolute. Just as stars fill the sky despite the void, so too do creatures inhabit the abyss despite the desert. The abyssal plains, covering more of Earth than forests, mountains or grasslands, are not barren after all. They are simply subtle, quiet and slow, worlds of patience rather than abundance. To understand them is to recognize that life does not always thrive in brightness or in plenty. Sometimes it thrives in scarcity, waiting patiently for whatever drifts its way. When we compare the abyss to space, the resemblance deepens in another way. Both are difficult to study, not only because of distance or depth, but because of scale. A spacecraft can capture a single image of a galaxy, but that image represents billions of stars across unimaginable space. An ROV can film a patch of abyss, but that patch represents thousands of square kilometers of unseen seafloor. In both cases, our knowledge is piecemeal. We glimpse, we infer, we imagine. The whole remains beyond us. Perhaps that's why the abyss captures curiosity. It's not dramatic in the way of hydrothermal vents or glowing creatures, but it is immense, and immensity commands respect. To think that most of our planet's surface lies here, hidden under miles of water, is to realise how little we truly know of our own home. The abyssal plains are not simply another environment. They are the environment, the dominant feature of Earth, invisible but vast. And so, while they may appear empty, they are anything but irrelevant. They regulate climate, sustain life, and preserve mystery. They are deserts not of lifelessness but of subtlety, requiring us to look closer, to notice more, to value what at first seems invisible. To cross them is impossible for us, but to imagine them is to understand a little more of the planet we live on. If the abyssal plains are the deserts of the deep, then the trenches are their canyons, gouged into the seafloor by forces far greater than anything we experience on land. They are the deepest scars on Earth, narrow valleys that plunge miles beneath the already sunless plain. To descend into one is to leave behind even the faint suggestion of openness, and to enter landscapes that are steep, confined, and almost unimaginable. They are Earth's hidden canyons, and though we've mapped their outlines, we've barely set foot within them. The most famous of these is the Mariana Trench in the Western Pacific. It stretches for more than 500 miles, longer than the distance from New York to Miami, and in places it plunges nearly 11 kilometers down. Challenger Deep, the lowest measured point, is the deepest known location on Earth. To put that in perspective, if Mount Everest were dropped into the trench, its peak would still be more than a mile underwater, and the Mariana is only one of many. There are trenches in the Atlantic, the Indian Ocean, and across the Pacific, each formed by tectonic collisions, each representing a meeting point between immense slabs of the Earth's crust. Where plates converge, one is forced beneath the other in a process called subduction. The result is a trench, a place where the seafloor folds downward into the mantle. These trenches are not only geological features, they are dynamic systems. Earthquakes rumble along their edges as plates grind against each other. Volcanoes form in nearby arcs, fueled by melting rock from the descending plate. Tsunamis are born from sudden shifts in their depths. In this way, the trenches connect directly to life on the surface, shaping continents and influencing disasters that ripple across oceans. To study them is not just to satisfy curiosity, it is to understand forces that shape our world. Yet for all their importance, trenches remain some of the least explored places on the planet. The extreme pressure makes entry dangerous, even with advanced technology. Only a handful of manned descents have reached Challenger Deep, and each was an engineering triumph. Most of what we know comes from remotely operated vehicles or from samples retrieved with weighted landers. And even then, knowledge is fragmentary. A trench is vast, with walls and valleys stretching for miles, and a single expedition can only touch one spot. It's as though we tried to understand the Grand Canyon by visiting a single ledge in the dark. What we have seen, however, is astonishing. Life exists even at these extreme depths. Amphipods, small crustaceans resembling shrimp, have been collected from Challenger Deep, some larger than their shallow water relatives, feeding on scraps of organic matter that drift down. In recent years, snailfish have been filmed in trenches more than 8 kilometers deep. Their bodies adapted to withstand pressures 1,000 times what we feel at sea level. These fish appear delicate, translucent, almost ghostly, yet they thrive where few others can. Microbial mats grow on rocks, feeding on chemicals seeping from the crust. Each discovery pushes the boundary of what we thought possible, and there are still mysteries. In 2017, scientists recorded a metallic ping sound deep in the Mariana Trench, a noise that did not match known species or geological activity. Some suspect an unknown whale call, others think it may be related to tectonic shifts, but no one can say for certain. The depths are filled with such puzzles, sounds, chemical traces, unexplained creatures glimpsed only briefly on camera. Each clue suggests that the trenches are not barren but active, alive with processes we barely understand. The trenches also play a crucial role in recycling Earth's crust. When plates are forced downward, they carry with them sediments, carbon, and even seawater, pulling these materials deep into the mantle. Over millions of years, some of this material re-emerges through volcanic eruptions. In this way, trenches are part of Earth's cycle of renewal, burying and remaking the crust itself. They are not static valleys, but conveyor belts of geology, constantly reshaping the planet. For humans, the difficulty of exploring them is part of their allure. To reach the bottom of Challenger Deep is to stand in a place fewer people have visited than have walked on the moon. The descent itself takes hours, the submersible sinking slowly through layers of darkness until at last it touches the sediment floor. The silence is total, broken only by the hum of machinery. Outside, the world is alien. The walls of the trench rise steeply, disappearing into blackness. The floor is covered in fine sediment, stirred by the landing. Perhaps a snailfish drifts past, pale and unhurried. To sit in such a place is to confront the enormity of the planet in a way few experiences can match, and yet, despite the danger, explorers return because every dive offers the chance to find something new. It might be a species never before recorded, a geological formation that reveals tectonic secrets, or simply the experience of touching the lowest point of Earth. Each discovery reminds us how little we know and how much waits below. The trenches also raise questions about pollution. Even here, in the deepest places, traces of human activity have been found. Plastic debris, chemical pollutants, and microplastics have been detected in trench sediments, and even inside amphipods collected from the depths. This is perhaps the most sobering discovery of all, that human influence extends even into the planet's most remote canyons. The trenches, once thought untouched, now bear witness to the reach of our species. They remind us that mystery and fragility often exist side by side. What makes trenches especially fascinating is how they concentrate extremes. Pressure here is beyond comprehension, yet life adapts. Darkness is absolute, yet creatures generate their own light. The geology is violent, yet ecosystems manage to persist. They are places where contradictions meet, and where survival takes forms we might never imagine if we hadn't seen them ourselves. It's tempting to think of the trenches as final frontiers, but in truth, they are only beginnings. Every sample pulled up, every image captured, opens new questions. What other organisms live there, beyond the reach of our cameras? How do these creatures reproduce, feed, and interact in such an environment? What geological processes operate at such depths, and how do they influence the surface world? Each answer leads to further mysteries, and each reminds us of the scale of what we have yet to learn. To picture the trenches is to imagine Earth turned inside out, its greatest depths revealed in narrow valleys that plunge far below the already vast ocean. They are canyons hidden beneath water, unseen by most eyes, yet essential to the planet's function. They are reminders that Earth holds landscapes as dramatic as any in space, waiting silently below. And perhaps that's their greatest lesson. We often look to the stars for wonder, imagining distant planets and uncharted galaxies, but the trenches show us that equally profound wonders lie here, on Earth, just beneath the surface. They are the hidden canyons of our planet, vast and deep, reminding us that mystery does not always lie far away. Sometimes it lies directly below, in the places we have not yet dared to go. When most people imagine the deep ocean floor, they picture stillness, a flat expanse of mud and silence, untouched for millennia. But scattered across that seemingly lifeless plain are places that defy the imagination. They are vents, fissures in the Earth's crust where seawater superheated by magma gushes back into the ocean, carrying with it minerals, metals and heat. They are called hydrothermal vents, and they are among the strangest features on the planet. To approach one is to encounter a world that seems to belong not to Earth, but to some other planet entirely. The discovery of hydrothermal vents in the late 1970s was one of the most shocking moments in modern science. Until then, the deep sea was assumed to be sparse and barren, dependent entirely on the trickle of organic matter drifting down from the surface. When scientists first lowered submersibles into the Galapagos Rift, they expected to see little. Instead, they found towering chimneys of black smoke spewing from the seafloor, surrounded by dense clusters of life. Giant tube worms, clams the size of dinner plates, and swarms of shrimp gathered in numbers no one thought possible in such darkness. It was an ecosystem unlike anything known before. The vents themselves are dramatic. Water seeps down into the seafloor, becomes superheated by magma, dissolves minerals, and then jets back out at temperatures exceeding 400 degrees Celsius. Despite this heat, the pressure of the deep ocean prevents the water from boiling. Instead, it bursts out as plumes of black or white smoke, depending on the minerals it carries. Black smokers emit sulfides of iron and other metals, forming towering chimneys as the minerals precipitate. White smokers release lighter materials like barium and calcium, creating smaller, paler structures. Both types create surreal landscapes of spires and plumes, vent fields that rise like alien cities from the seafloor. What makes these vents extraordinary is not just their geology, but their biology. Around them thrive organisms that rely not on sunlight, but on chemistry. Bacteria use hydrogen sulfide, a toxic gas to most life, as fuel, converting it into energy through a process called chemosynthesis. These bacteria form the base of a food web that sustains entire communities. Tube worms, with their long red plumes, house the bacteria inside their bodies, exchanging chemicals for nutrients. Clams and mussels filter bacteria from the water. Crabs and shrimp graze on microbial mats. Fish and octopuses hunt among them. It is an entire ecosystem, independent of the sun, surviving entirely on the chemical energy of the Earth. This discovery overturned assumptions about life. Until then, sunlight was considered essential, the foundation of all ecosystems. The idea that life could thrive without it, in complete darkness, fed by chemicals from the Earth's crust, was revolutionary. It expanded the definition of habitability and offered a glimpse into how life might exist elsewhere in the universe. If it can survive at vents in the deep ocean, perhaps it can survive in subsurface oceans on icy moons, warmed by tidal heating and chemical reactions. Europa, Enceladus, and other worlds suddenly seemed more likely to harbour life. Hydrothermal vents became not just a discovery of Earth's biology, but a template for extraterrestrial possibilities. The creatures of the vents are as strange as their environment. Tube worms can grow more than 2 meters long, their bodies containing no mouths or digestive tracts. Instead, they rely entirely on symbiotic bacteria. Their blood contains special molecules that bind hydrogen sulfide without poisoning the organism, delivering it safely to the bacteria. Vent shrimp often have light-sensitive patches on their backs, possibly adapted to detect the faint glow of hot vent water. Some species cluster so densely that they cover vents in writhing layers, feeding on microbes. In this world, survival is not about photosynthesis or grazing, but about partnership with microbes that transform poison into life. The vents are also dynamic. They can spring up suddenly where tectonic activity opens new fissures, and they can die just as quickly when activity shifts. Some last only decades, others centuries. This instability forces life to adapt not only to extremes of temperature and chemistry, but also to sudden change. Species may colonize new vents quickly, dispersing across the seafloor through larval stages that drift in currents. In this way, vent communities are both fragile and resilient, vulnerable to local collapse but capable of re-establishing themselves elsewhere. For scientists, vents provide clues about the origins of life itself. Some theories suggest that early life on Earth may have arisen around similar systems billions of years ago. The combination of heat, minerals, and chemical gradients could have created conditions where simple molecules assembled into complex ones. The presence of energy sources independent of the sun means that life could have started in the deep, sheltered from harsh surface conditions. Studying vents today is, in a sense, studying the possible cradle of life. Vents are also important to geology and chemistry. The minerals they emit create unique deposits of metals like copper, zinc, and gold. Over geological timescales, these contribute to the formation of ore deposits mined on land today. Some companies are even exploring the possibility of mining active vent fields, drawn by their richness. But such exploitation raises concerns. Vent ecosystems are delicate and may take centuries to recover from disturbance. Destroying them for short-term gain risks erasing unique habitats that could teach us about resilience, evolution, and even the origins of life. Exploration of vents continues to reveal surprises. In 2016, scientists discovered a massive vent field in the Indian Ocean, with chimneys taller than the Empire State Building. In 2020, a new species of pancake crab was found near vents, adapted with flattened bodies to squeeze into tight spaces. Each expedition uncovers organisms never seen before, suggesting that vent ecosystems may rival rainforests in diversity, even though they occupy tiny patches of the seafloor. The combination of extremity and abundance makes them one of the most fascinating habitats on Earth. But perhaps what is most striking about vents is the contrast they present. Just meters away from boiling hot, mineral-rich plumes, the surrounding ocean is near freezing. Creatures huddle in dense clusters around the chimneys while the plains beyond remain sparse. Life here exists in sharp boundaries, thriving in places that seem uninhabitable, while avoiding areas that seem more forgiving. It is a reminder that habitability is not always about comfort, but about opportunity. Where energy exists, life will find a way to use it. For those who have seen vents in person, whether through submersibles or video feeds, the impression is unforgettable. Towering black smokers rising from the seafloor, plumes billowing upward like underwater volcanoes, creatures clustered in impossible abundance, glowing shrimp darting through the haze. It feels less like Earth than like an alien landscape. And yet, it is Earth, one of its most dynamic and overlooked environments, hidden just out of sight. The mystery of hydrothermal vents is not only about what they are, but about what they suggest. They suggest that life is versatile, that it can emerge in conditions we once thought impossible. They suggest that the Earth is far more dynamic beneath the surface than we often remember. And they suggest that other worlds, far from our sun, may harbour life in places just like this. In every way, vents expand our sense of the possible, and so, from the desert of the abyssal plains and the steep walls of the trenches, we arrive at these improbable oases of heat and chemistry. They are not common, but they may be among the most important discoveries of the last half-century. They remind us that Earth still holds surprises capable of reshaping science, and that the deep sea is not simply a place of scarcity, but also of abundance in the most unlikely forms. When the last rays of sunlight vanish and the ocean turns to complete night, you might expect only emptiness. But instead, something remarkable happens. In the deep, where light from above cannot reach, life itself becomes the source of illumination. Tiny sparks, slow pulses, sudden flashes, steady glows, all flicker through the water as if the sea has grown its own stars. This phenomenon is called bioluminescence, and it is among the most widespread adaptations in the ocean. It is also one of the most breathtaking. Bioluminescence is light produced by living organisms through chemical reactions. In most cases, a molecule called luciferin reacts with oxygen in the presence of an enzyme called luciferase, releasing energy in the form of light. The exact chemistry varies across species, but the result is the same: cold light that doesn't waste energy as heat. Unlike a flame, which burns hot, bioluminescent light is efficient, perfectly suited for life in the deep, and it isn't rare. By some estimates, more than 3/4 of deep-sea organisms can produce light in some form. From tiny plankton drifting near the surface to the most alien fish of the abyss, the deep ocean glows. The purposes of bioluminescence are as varied as the creatures that use it. For some, it is a lure. The anglerfish, with its famous glowing appendage, dangles a beacon in the dark. Small fish, curious or hungry, approach the glow only to find themselves swallowed in an instant. For others, it is camouflage. Many fish and squid use counter-illumination, producing light on their undersides that matches the faint glow from above, erasing their silhouettes. Seen from below, they vanish into the background. For still others, it is a defense. Some shrimp and squid release glowing clouds of bioluminescent fluid, startling predators and giving them time to escape. Jellyfish may flash suddenly when disturbed, startling attackers or drawing the attention of larger predators to their own predators. In some cases, bioluminescence is communication. Certain species of lanternfish produce patterns of light unique to their kind, possibly used to attract mates or signal territory. Firefly squid in Japanese waters gather in immense numbers during spawning season, lighting up the coast with their blue glow. Even in the darkness of the deep, light remains a universal language. The difference is that here, the words are written in flashes and sparks rather than in speech. What makes bioluminescence so striking is not just its function, but its beauty. Imagine descending into the midnight zone in a submersible. Outside the glass it is black, the kind of black that feels endless. And then, suddenly, points of light begin to appear. Some drift slowly, glowing faintly. Others flash briefly, like distant lightning. Occasionally, a larger creature passes by, its body glowing in patterns across fins or tentacles. The effect is like drifting through a field of stars, except these stars are alive, moving, hunting, signalling, surviving. It is both alien and strangely familiar, a reminder that light has always been the language of life, whether from the sun above or the creatures below. Bioluminescence also reveals how creative evolution can be. Different groups of organisms, fish, squid, shrimp, jellyfish, even bacteria, have all developed it independently. This suggests that light is such a powerful advantage in darkness that nature has reinvented it many times. The chemistry differs, the organs differ, but the result is always the same: light in the dark. Convergent evolution, where unrelated species develop similar traits, is often a clue to importance, and in the deep sea, light is clearly vital. One of the most extraordinary displays of bioluminescence happens not in the abyss, but nearer the surface, where plankton create glowing waves. In certain places, such as bays in Puerto Rico or along the coasts of the Maldives, swimmers at night can create trails of glowing blue as they disturb the water. These plankton, called dinoflagellates, light up as a defense mechanism, possibly to attract predators to whatever is attacking them. To humans, the effect is magical. Water that seems alive with stars, every movement painted with light. Though shallow compared to the deep, these displays hint at the abundance of bioluminescence throughout the ocean. In the deep itself, the variety is endless. The stoplight loosejaw, a type of dragonfish, produces red light, invisible to most other creatures but visible to its own specialized eyes. This gives it the equivalent of night vision goggles in the dark, letting it illuminate prey that cannot see it coming. The cookie cutter shark uses bioluminescence to disguise itself, glowing along most of its body but leaving a dark patch underneath. To larger predators, it resembles a small fish. When they approach, the shark strikes, biting out circular chunks of flesh. Even parasites and bacteria use bioluminescence, glowing inside hosts or forming symbiotic relationships where their light benefits both partners. Scientists studying bioluminescence face unique challenges. Many creatures lose their glow when stressed or removed from pressure. Some require specific chemicals in the water to produce light. Observing them in their natural environment often means using cameras sensitive enough to capture faint glimmers without disturbing the animals with artificial lights. Each glimpse requires patience, yet every glimpse reveals something extraordinary. Footage of comb jellies pulsing with rainbow light, of squid releasing glowing ink, of tiny fish blinking like fireflies. It all adds to the growing picture of a world that is not dark but alive with its own constellations. Beyond beauty, bioluminescence also plays a role in science and medicine. The proteins that cause glowing reactions have been adapted for use in laboratories, allowing scientists to track genes, study disease, and develop treatments. A jellyfish protein called GFEP, green fluorescent protein, has become one of the most important tools in modern biology, earning a Nobel Prize for the researchers who developed it. In this way, the stars of the ocean deep contribute not just to survival underwater, but to human knowledge above. The comparison to stars is more than metaphorical. Just as stars light the night sky, bioluminescent organisms light the ocean night. Both remind us that darkness is rarely absolute. Wherever there is life, light finds a way, and both inspire awe. To look at a galaxy filled with stars is to feel small in the universe. To look at a sea filled with glowing creatures is to feel small within our own planet. The scale is different, but the effect is the same. Both are reminders of beauty, persistence, and the power of life to adapt. There is still so much we don't know. How many species use bioluminescence? What patterns of light mean to them? How ecosystems shape and are shaped by these signals? Each expedition uncovers more, yet the mystery remains vast. Perhaps that is fitting. Stars, after all, are best admired when they still hold secrets. The same may be true of the stars of the sea. And so, when we think of the deep as empty, we must remember this. It is not empty, but filled with light created by life itself. Not sunlight, but starlight of another kind. It is a universe of its own, with galaxies of glowing fish, constellations of drifting plankton, and supernovas of flashing squid. It is a reminder that life, when faced with darkness, doesn't retreat. It shines. If outer space has rockets, capsules, and rovers, then the deep sea has its own fleet of machines, each designed to endure an environment as hostile as any distant planet. They are submersibles and robots, our spaceships for the sea, and without them the deep would remain hidden forever. For all the wonder of what we've seen in trenches, vents, and abyssal plains, every image, every sample, every glimpse has depended on these machines. They are the eyes and hands we send into the depths, vessels built to withstand pressure, silence, and darkness that human bodies could never survive. The first attempts to explore beneath the surface were crude. In the early 20th century, divers used heavy suits with air pumped down from the surface, but their range was limited to shallow depths. Beyond a few hundred feet, pressure became too great, and the hoses too unreliable. It wasn't until the invention of the bathysphere in the 1930s that humans made their first true descent into the deep. The bathysphere was a steel sphere barely large enough to fit 2 people, suspended from a cable and lowered slowly into the sea. William Beebe and Otis Barton used it to reach more than 900 meters, far deeper than anyone had ever gone before. From their small window, they described fish that glowed, jellyfish that shimmered, and creatures no one had ever imagined. The bathysphere was primitive with no power of its own, dependent entirely on the cable from the surface, but it proved something crucial, that humans could descend into the deep and return. Later came the bathyscaphe, a new kind of submersible that carried its own buoyancy and ballast. Auguste Piccard designed the first of these, and in 1960 his son Jacques, along with Don Walsh, piloted the bathyscaphe Trieste into the Mariana Trench. Their descent to Challenger Deep remains one of the most famous moments in ocean exploration. Inside a pressure sphere suspended beneath a float filled with gasoline for buoyancy, they dropped nearly 11 kilometers into darkness. The windows were tiny, the cabin cramped, and the descent took hours. When they reached the bottom, They saw the seafloor for 20 minutes before rising again. It was a triumph of engineering and courage, and it showed that the deepest places on Earth were not beyond human reach. Since then, technology has advanced dramatically. Modern submersibles are far more manoeuvrable, equipped with robotic arms, high-definition cameras, and instruments capable of analysing water and sediment. Some, like Alvin, operated by the Woods Hole Oceanographic Institution, have been in service for decades, making hundreds of dives and contributing to discoveries such as the first hydrothermal vents. Others, like James Cameron's Deep Sea Challenger, were built for one mission: to reach the trench and return. Each represents a blend of human curiosity and technological ingenuity, designed to carry fragile bodies into a realm of crushing force. But as much as we marvel at crude submersibles, most exploration today is done by robots. Remotely operated vehicles, or ROVs, are tethered to ships by long cables that carry power and transmit data. They can stay down for hours or even days, sending back live video feeds, collecting samples with robotic arms, and hovering in place with precision thrusters. Their cameras reveal colours our eyes would never see unaided in the dark. Their sensors measure temperature, pressure, and chemistry. Their claws retrieve rocks, corals, and strange creatures for study. ROVs like Jason, Hercules, and Victor have mapped vast areas of the ocean floor and discovered species that no human eyes had ever seen. Then there are autonomous underwater vehicles, or AUVs. Unlike ROVs, they are not tethered. They roam freely, following pre-programmed paths or reacting to conditions they detect. They can map seafloor terrain with sonar, measure currents, and even hunt for signs of life around vents. Some are small, shaped like torpedoes, while others are large and complex, capable of missions lasting weeks. AUVs represent the oceanic equivalent of space probes, machines that go where humans cannot, gathering data quietly and tirelessly. These machines face challenges every bit as daunting as spacecraft. Pressure is constant, threatening to crush any weakness. Salt water corrodes metal and electronics. Communication is limited, with signals slowed or blocked by water. Power is finite, requiring careful management of batteries or connections to surface ships. And recovery is always uncertain. A storm, a snag, or a malfunction can end a mission abruptly. Yet despite these risks, submersibles and robots have become the backbone of deep-sea exploration, allowing us to see what would otherwise remain unseen. Inside a manned submersible, the experience is both exhilarating and claustrophobic. The cabins are small with little room to move. The walls are thick spheres of metal designed to hold back the crushing sea. Windows are no larger than dinner plates, and outside those windows is blackness interrupted only by what the submersible's lights reveal. There is no sense of scale, only what the beams can touch. A fish passes, its body glowing faintly. A crab scuttles across the sediment. A plume of hydrothermal smoke rises like a shadow. To sit there is to feel suspended between worlds, safe inside a fragile bubble, while outside lies a realm utterly indifferent to your presence. For operators of ROVs, the experience is different but no less profound. They sit aboard ships piloting their machines remotely, watching video feeds that reveal landscapes miles below. Joysticks control robotic arms that delicately grasp corals or scoop sediments. Monitors show readouts of temperature and chemical signatures. It is exploration at a distance, mediated by machines, yet the excitement is real. Each moment of discovery arrives as if from another world, transmitted through fibre optic cables stretched across the sea. The development of these machines has transformed our understanding of Earth. Without them, we would never have seen the vents, never have discovered life in trenches, never have mapped the contours of the abyss. They're not just tools, they're extensions of ourselves, translating human curiosity into action where our bodies cannot go. In that sense, they are indeed spaceships for the sea, carrying our imagination into a realm as foreign as any planet. Yet for all the progress, limitations remain. Manned dives are rare and expensive. ROVs cover limited areas at a time. AUVs, though capable of long missions, cannot yet match the adaptability of human eyes and judgment. The ocean remains vast, and our machines explore only fragments. What we know is extraordinary, but it is still the beginning. In the future, new designs may change that. Advances in robotics, artificial intelligence, and materials could allow machines to explore more widely, more deeply, and for longer periods. Some envision fleets of small AUVs working together, mapping the ocean in detail. Others imagine permanent observatories on the seafloor, sending back data continuously. There is even talk of swarms of micro-robots, drifting like plankton, each carrying sensors to measure the environment. If realized, these could transform our understanding of the sea as profoundly as telescopes transformed our view of space. But even as machines advance, there is something irreplaceable about human presence. Astronauts in orbit inspire because they are fragile bodies in an unforgiving void. Divers in submersibles inspire for the same reason. To know that a person has sat at the bottom of the world, surrounded by crushing blackness, is to feel the courage and ingenuity of exploration. Machines may do most of the work, but humans provide the meaning. Each submersible dive is a reminder that curiosity is not only mechanical, it is deeply human. When we call submersibles and robots our spaceships for the sea, it is not only a metaphor. The parallels are real. Both space and deep-sea machines face hostile environments. Both require sealed cabins, pressure vessels, and life support systems. Both struggle with communication delays and power limitations, and both serve the same purpose: to extend our reach into realms we cannot survive unaided. The ocean and the cosmos may seem different, but the machines we build for each reveal their kinship, and so, every glowing image of a vent, every glimpse of a snailfish, every map of the abyssal plain comes to us because of these machines. They are the reason we know the deep is not empty but alive. They are the reason we can imagine life beyond Earth with more confidence. They are in every sense our vehicles into the unknown. For all our ingenuity, for all the machines we've built and the dives we've made, the ocean continues to resist us. Every attempt to explore it feels like a negotiation with an environment that would rather remain unseen. We push against its barriers, but the sea pushes back with darkness, pressure, cold, and distance, reminding us that curiosity alone is never enough. Unlike space, which opens wide above us, the ocean is heavy, crushing, and unwilling to yield easily. It is not empty, but full of obstacles that slow us down, limit our reach, and remind us of our fragility. The first challenge is obvious: pressure. It increases relentlessly, about 1 atmosphere for every 10 meters of depth. At 100 meters, the pressure is 10 times what it is at the surface. At 1,000, it's 100 times greater. By the time you reach the bottom of the Mariana Trench, the weight of 1,000 atmospheres presses in on every surface. Machines must be built to withstand this force, and people cannot endure it at all without protection. It means that every dive requires engineering precision. A small flaw in the hull of a submersible could mean disaster. The ocean leaves no margin for error. Then there is the problem of darkness. Light fades quickly, absorbed by water within the first few hundred meters. Beyond that, even the most powerful beams cannot illuminate far. Submersibles travel with spotlights, but these create narrow cones, leaving the surroundings in blackness. It's like exploring a vast cave with a flashlight. What you see is detailed, but what you don't see is immeasurable. Cameras can capture what lights reveal, but the scale of the ocean means most of it remains hidden. Unlike telescopes, which can scan the heavens in broad swathes, our tools underwater reveal only fragments. Cold is another barrier. At depths beyond a few hundred meters, temperatures hover just above freezing, rarely rising above 4 degrees Celsius. For machines, This means electronics must be insulated and materials must endure contraction. For life, it means slow metabolisms, careful energy use, and adaptations that often seem alien. For humans, it means survival requires total enclosure. Divers in suits cannot endure it for long, and submersibles must maintain steady internal environments to keep crews alive. Cold by itself may not seem as dramatic as pressure, but it shapes everything about the deep sea and how we reach it. Communication is equally difficult. On land and in space, we rely on radio waves to transmit signals, but radio does not travel well through water. Signals fade within meters, forcing submersibles to rely on acoustic methods, sound pulses that travel farther but much more slowly. A message sent to a deep robot may take seconds to arrive, and the return may be distorted or delayed. This makes remote operation challenging, requiring patience and prediction rather than instant control. In space, communication with a probe on Mars involves delays of minutes, but the data stream is steady and clear. In the ocean, signals degrade, bounce and shift, forcing operators to work with fragmentary information. Then there is the sheer scale of the ocean. It covers 70% of Earth's surface and holds an average depth of nearly 4 kilometers. To map it in detail is a task so enormous, it borders on the impossible. Sonar can provide broad outlines, but to create high-resolution maps would require centuries of continuous surveying. Every expedition covers only tiny patches, leaving most of the seafloor unseen. When you think about how easily we can zoom into a street corner on Earth with satellites, it becomes startling to realise how little of the ocean floor has been imaged in the same way. The resistance here is not just physical but logistical. The sea is too large, too deep, too hidden for us to conquer quickly. Cost compounds the challenge. Space programs capture public imagination and attract billions in funding. Ocean exploration rarely inspires the same investment. Submersibles are expensive to build and operate. Research ships require crews, fuel, and months at sea. Each dive represents years of preparation, and even then, results may be limited to a few hours of footage or samples. When funding is scarce, priorities turn elsewhere. It isn't that we lack the technology to study the ocean more, it's that we rarely choose to devote the necessary resources. In this way, the resistance is not only natural, but human. The unpredictability of the sea adds another layer. Weather can cancel expeditions, storms can force ships to retreat, currents can push submersibles off course, sediment stirred by thrusters can obscure cameras, equipment can fail under pressure or corrode in salt water. Every mission is vulnerable to setbacks, and success is never guaranteed. Scientists often spend years planning dives only to lose valuable hours to technical problems or rough seas. The ocean does not offer stability. It demands flexibility, patience, and acceptance of failure. Even when machines succeed, the creatures of the deep resist study. Many are fragile, collapsing when brought to the surface. Others die when pressure decreases, their bodies unable to function in our environment. Bioluminescence fades outside its natural context. Behaviour changes when artificial lights and noise intrude. In many cases, what we see is only a distorted version of reality, a shadow of life as it truly exists. This makes the ocean not only resistant to entry, but resistant to understanding. We can visit, but we alter what we touch. It's worth remembering too that exploration is never just about tools, it's about risk. Astronauts in orbit rely on technology to survive, but they also rely on courage. The same is true in the sea. To sit inside a submersible, surrounded by thousands of meters of water, aware that one failure could mean instant death, requires not only engineering but trust. Every deep dive carries danger, and every diver knows it. The resistance of the ocean is not abstract. It is personal, pressing on the hull, audible in every creak of metal, present in every groan of machinery. And yet, for all these barriers, the ocean's resistance is part of its allure. Mystery is preserved by difficulty. Secrets survive because they are hard to reach. If the deep were easy, It would have been mapped long ago, its creatures catalogued, its processes understood. Instead, its very resistance keeps it alive as a frontier. It slows us, forces us to build better machines, demands patience, and ensures that wonder does not vanish too quickly. The ocean resists us, and in doing so, it protects its mysteries. Perhaps that is why each discovery feels so profound. A glimpse of a snailfish at 8 kilometers, a video of a giant squid, a map of a vent field. These are small things compared to the scale of the ocean, but they carry weight because they are so hard won. Each represents years of effort against pressure, darkness, cold, distance, and cost. Each is a triumph against resistance. The ocean never gives easily, but when it does, it rewards us with revelations, and so we continue to push. We build better submersibles, more capable robots, and longer-lasting sensors. We imagine fleets of autonomous machines, permanent observatories on the seafloor, even future technologies we cannot yet name. We push not because the ocean allows us, but because it resists. Its very refusal to yield compels us to try, and perhaps that is the deepest truth. Exploration is not about what gives easily, but about what refuses. When people think of the deep sea, they often imagine strange fish or towering vents, but another layer of mystery lies scattered across its floor. Lost worlds and ancient wrecks, remnants of human history preserved in darkness. The ocean doesn't just conceal ecosystems we've barely begun to study. It also conceals our own stories, forgotten voyages, vanished ships, planes that never returned, and artifacts that connect us to lives long past. These relics lie under the same pressure and silence that hide living creatures, but unlike biology, they tell us something about ourselves, about our journey across time and water. The sea has always taken what it wants. Storms have dragged down fleets. Reefs have torn holes in wooden hulls. Torpedoes and battles have left steel graveyards on the seafloor. Once gone, these vessels often vanish completely from memory, their fates unknown except to those who went down with them. But centuries later, machines return to find them again. Submersibles and remotely operated vehicles glide through the dark, their lights cutting across timbers or steel beams, illuminating ships that look frozen in time. Cannons still mounted, shoes still scattered across decks, porcelain plates lying unbroken in sediment. The effect is haunting. Among the most famous discoveries was the Titanic. For decades, its location was a mystery. After it sank in 1912, carrying over 500 lives, the exact coordinates remained lost, buried beneath myths and speculation. It wasn't until 1985, when Robert Ballard and his team used advanced sonar and submersibles, that the wreck was finally found nearly 4 kilometers below the surface. What they saw stunned the world. The bow upright, recognizable, draped in rusticles formed by iron-eating bacteria, the stern shattered by impact, debris spread for miles. For the first time, the story became visible again. The Titanic wasn't just a tale, it was a presence, lying silent in the dark. But the Titanic is only one ship among thousands. In the Pacific, the remains of a naval battle still rest on the seafloor. Aircraft carriers, submarines, fighter planes, all preserved by the cold. In the Mediterranean, ancient trade ships lie with amphorae still stacked, once filled with olive oil or wine. Each wreck is a capsule of history, a frozen moment when life shifted from movement to silence. Unlike ruins on land, which weather and erode, wrecks in the deep often remain surprisingly intact. Without currents, scavengers, or sunlight, wood and metal can last centuries. In some cases, leather shoes or textiles survive, sheltered in sediment. To look at them is to feel the proximity of the past. Explorers sometimes describe the eerie stillness of visiting these wrecks. Submersibles hover near decks once crowded with sailors, now empty. Robotic arms brush sediment from an object last touched hundreds of years ago. Unlike a museum, there is no barrier of glass, no reconstruction. The objects are exactly where they fell. That rawness makes the experience both powerful and unsettling. You aren't just studying history, you're entering it, surrounded by it, immersed in its silence. Beyond ships, the deep sea also holds lost landscapes. During the last ice age, sea levels were far lower, exposing vast regions now drowned. Coastlines stretched farther, rivers cut valleys across what are now continental shelves, and human settlements may have stood where today waves roll overhead. As glaciers melted and seas rose, these worlds vanished. Today, sonar mapping occasionally reveals their outlines, ancient riverbeds, shorelines, even possible sites of habitation. Archaeologists call this area the drowned landscapes, and they may hold keys to understanding early human history. Entire chapters of migration, settlement, and culture could lie buried beneath the sea. Finding them, however, is as difficult as exploring trenches or vents. Sediments bury structures, currents erode evidence, and the sheer scale of the seafloor makes searching painstaking. Yet occasional discoveries hint at the richness of what lies below. Stone tools found on submerged shelves suggest ancient camps. Fossilized forests preserved underwater reveal ecosystems from ages past. In rare cases, structures resembling walls or pillars spark debates about whether they are natural or human-made. Each discovery adds to the possibility that much of human prehistory is hidden not on land but underwater, awaiting the tools to reveal it. Wrecks also serve as artificial reefs. Over time, corals colonize steel and wood, fish gather in the shelter of beams, and ecosystems emerge. A warship becomes a reef, a plane becomes a home for eels, a cargo vessel becomes a gathering point for schools of fish. Life reclaims what humans lost, folding history into biology. For divers and scientists, this creates a strange duality. A wreck is both grave and habitat, both memory and present. To study it is to see the intertwining of human history and natural adaptation. There's also the moral question of how we treat these places. Many are war graves, final resting places for those who went down with their ships. Some argue they should remain untouched, preserved as memorials rather than salvaged for relics. Others see value in recovering artifacts to preserve them on land. The balance is delicate. Technology allows us to reach deeper and recover more, but with that ability comes responsibility. The ocean resists us, but when it yields, we must decide how to act. In some ways, exploring wrecks feels different from exploring vents or trenches. The latter reveal the unknown workings of Earth, systems beyond us. Wrecks, by contrast, reflect us back to ourselves. They show our ingenuity, our ambition, our failures, our tragedies. They remind us that the sea has always been a place of risk, a frontier where progress and loss are entwined. To descend to a wreck is to meet ghosts, not in a supernatural sense, but in the sense of encountering lives abruptly ended and stories cut short. The silence of the deep amplifies that encounter. Technology has transformed what we can see. High-definition cameras mounted on ROVs now capture wrecks in astonishing detail, creating 3D models that allow archaeologists to explore them virtually. Sonar scans reveal outlines buried in sediment. In some cases, divers still visit shallower wrecks, though always with limits. But for the deepest, robots are the only way. Each new wreck found adds to the catalogue of human history preserved in water. Some are famous names, like the Titanic or the Bismarck. Others are anonymous merchant ships, their crews forgotten, their stories untold. Yet each matters. Each is a piece of the human journey scattered across the seafloor. The ocean also preserves modern losses. Planes lost in war, ships sunk in storms, even cargo containers dropped accidentally. These too settle into the dark, joining the older wrecks. Future explorers may look at them as we look at amphorae, seeing them not as tragedies but as artifacts of an earlier age. The sea does not distinguish between ancient and modern. It takes everything, holds it, and transforms it into part of its silent archive. For all the technological triumphs of finding and studying these sites, there is still something profoundly humbling about them. We often approach the ocean as a frontier of discovery, a place to expand our knowledge of life and geology. But the wrecks remind us that the ocean is also a frontier of forgetting, of loss, of humility. It has taken more from us than we have taken from it, and its depths are filled with reminders that human mastery is always incomplete. To think of the deep sea only in terms of biology or chemistry would miss this entirely. It is also a graveyard, a museum, a library of histories we cannot read fully. It holds not only strange creatures and alien landscapes, but also our own echoes preserved in darkness. These lost worlds and ancient wrecks are proof that the ocean is not separate from human life. It is entwined with it, shaping and recording our passage, keeping our memories in silence until curiosity leads us back to them. If the abyssal plains are deserts and the trenches are canyons, then the ridges and volcanoes hidden beneath the sea are its mountains. They rise from the seafloor in vast chains, stretching across the globe in ways that dwarf anything we know on land. Unlike the Alps or the Andes, though, these ranges remain mostly unseen, covered by kilometers of water. They are mountains that whisper rather than shout, volcanoes that erupt in silence, ridges that build continents while hidden from view. To speak of Earth's geography without them is to tell only half the story. At the centre of it all is the mid-ocean ridge system, the longest continuous mountain chain on Earth. It winds for more than 60,000 kilometres around the planet, circling like a seam on a baseball. From the Arctic to the Southern Ocean, from the Atlantic to the Pacific, this ridge is the backbone of the seafloor. Here, tectonic plates pull apart, and molten rock wells up to create new crust. Slowly, steadily, the ocean floor spreads, pushing continents apart and reshaping Earth's surface over millions of years. It is geology in motion, hidden under waves. What makes these ridges extraordinary is their scale. On land, the Himalayas seem enormous, their peaks towering into the sky. But the mid-ocean ridge system is more than 20 times longer. Its peaks may not pierce the air, but in sheer length and global impact, no mountain range compares. And unlike land ranges, it is not static. It is constantly active, creating new crust as magma emerges and hardens, building the very ground on which oceans rest. Every inch of seafloor was born this way, at some point in time, at some point along this global ridge. Volcanoes are scattered across this system. Some are small vents, releasing lava quietly. Others form massive undersea mountains called seamounts, some of which rise high enough to break the surface and form islands. Hawaii, Iceland, the Azores, all are the visible tips of volcanic systems that extend far below. For every island we see, there are thousands of seamounts that never broke the surface, hidden peaks rising from the abyss. In fact, estimates suggest there may be more than 100,000 seamounts in the ocean, each a volcano in its own right. Some are extinct, others still active, their eruptions shaping the seafloor in ways we are only beginning to map. What happens at these ridges and volcanoes is not just geological but biological. The same forces that create new crust also drive hydrothermal vents, where seawater seeps into the seafloor, heats, and rises again carrying minerals. Around these vents, we find entire ecosystems independent of sunlight. In this way, mountains and ridges not only shape geology but also life, creating oases in the deep where bacteria, tube worms, shrimp, and countless other species gather. Without the heat of volcanoes, these ecosystems would not exist. Eruptions underwater look different from those on land. Instead of fiery fountains and clouds of ash, lava meets water and cools almost instantly, forming pillow-like shapes called pillow basalts. Over time, these pile up into ridges and slopes. In some cases, eruptions are explosive, blasting ash and gas into the sea, but the water dampens sound and light, making them invisible from the surface. It's a quiet drama, geology performed out of sight. Only with sensors and cameras do we witness it, seeing new crust form in real time. To scientists, these moments are extraordinary, glimpses of processes that usually happen too slowly to perceive. Seamounts and ridges also shape ocean currents. Their slopes deflect water, creating turbulence that stirs nutrients and influences circulation. This mixing helps sustain marine life, bringing nutrients from the deep upward where plankton can use them. In this way, the mountains of the sea are not just geological features, but engines of the biosphere, connecting deep processes to surface life. Without them, the ocean's circulation would be weaker and its ecosystems poorer. Exploring these mountains is as challenging as exploring trenches. Their slopes are rugged, their summits hidden. Sonar mapping reveals outlines, but details remain scarce. Submersibles can climb their sides, but only in narrow bands. ROVs can capture footage, but the scale is so vast that no single mission can capture more than fragments. Imagine trying to understand the Rockies by filming a few hundred meters of slope. You would miss the grandeur, the connections, the continuity. That is how we approach the mid-ocean ridge system, glimpses of a giant. Yet those glimpses are powerful. When scientists filmed an eruption on the seafloor for the first time in the 1990s, it was a revelation. Lava gushed, water boiled, vents hissed, all happening miles below the surface, completely unnoticed by the world above. It reminded us that Earth is alive beneath our feet, constantly reshaping itself, even when hidden by oceans. That activity is not rare. Eruptions happen along the ridge system regularly. They simply occur out of sight. Some seamounts become hotspots of life. Corals colonize their slopes, forming deep-sea reefs that last for centuries. Fish gather in their currents, making them rich fishing grounds. Whales migrate along their paths, using them as waypoints. In this sense, underwater mountains act like islands in the sea, gathering life around them. But unlike islands, most are invisible, their importance unrecognized until sonar or exploration reveals them. Protecting them has become a priority, as fishing and mining threaten to strip them before we understand their role. Volcanoes beneath the ocean also remind us of the planet's interconnectedness. An eruption at sea can trigger tsunamis, shaking coasts thousands of miles away. Ash and gases released can alter water chemistry. Over millennia, ridges and volcanoes push continents apart, create basins and shape the map itself. Without them, Earth would be unrecognizable. They are not marginal features, they are central, and still they whisper. Their eruptions are muffled by water, their mountains are hidden, their ridges stretch unseen across the globe. Only by listening with instruments, by mapping with sonar, by descending in machines do we hear them. They are the mountains that shape our world, but remain almost entirely invisible. For explorers, to visit one is to experience both awe and humility. Submersibles rise along slopes that disappear into darkness above and below. Lights reveal cliffs, lava formations, clusters of life. A vent chimney towers, smoking gently in the current. A crab scuttles across fresh basalt. It feels like visiting a new planet, but it is our own. Every ridge, every volcano, every seamount reminds us that Earth is not finished. It is still building, still moving, still alive. Perhaps the greatest challenge is simply comprehending the scale. To say that the mid-ocean ridge is 60,000 kilometers long is a number, but not an image. To imagine it is to picture a mountain chain circling the Earth, hidden underwater, always active, always creating. To realize it exists is to see Earth as a planet not of land but of sea, its geography shaped more by what lies beneath than what rises above. And so, as we move from the plains to the trenches, from wrecks to vents, we arrive at these whispering mountains. They are less dramatic in story than the Titanic or the giant squid, but in importance, they may surpass them all. They are the backbone of the planet, the quiet builders of continents, the unseen architects of oceans. Their whispering voices are felt in every coastline, every current, every map. To understand them is to understand Earth itself. When people hear the name NASA, they think of rockets rising above the clouds, astronauts floating in orbit, or robotic probes crossing the void between planets. But NASA also turns its attention downward, into the ocean, because the deep sea is the closest alien world we have without leaving Earth. To study it is to practice for other planets and moons, to train our eyes, our instruments, and our imagination for the day when we finally encounter the unknown beyond Earth. The ocean is not just water. It is a laboratory for space exploration, and it has become one of NASA's most valuable analogues for alien environments. The connection might seem surprising at first. What could a dark, crushing, water-filled abyss have in common with space? But the similarities are striking. Both are extreme environments where humans cannot survive without machines. Both demand vessels that withstand pressure, outward in space, inward in the sea. Both are hostile to life as we know it, yet both hold the potential for discovery. In fact, for engineers and scientists, designing a submersible and designing a spacecraft often feel like variations of the same challenge. Build a machine that can protect fragile human bodies in a place that wants to destroy them. The parallels deepen when you think about exploration. Sending a rover across Mars requires operating it remotely, dealing with communication delays, and interpreting limited data. Sending an ROV into the deep sea is similar. Signals degrade, time lags occur, and operators must make decisions based on fragments of information. Both environments force creativity, patience, and the ability to adapt when machines fail far from home. The ocean is not only practice for building machines, it's practice for building resilience in explorers. NASA's interest in the ocean is most evident in its work on astrobiology, the study of life beyond Earth. When hydrothermal vents were discovered in the 1970s, thriving with communities of life that did not depend on sunlight, the implications for space were immediate. If life could exist in complete darkness, powered by chemistry instead of photosynthesis, then it could also exist beneath the icy crust of moons like Europa or Enceladus. These moons are believed to hold subsurface oceans in contact with rock, heated by tidal forces and perhaps venting minerals into water. In other words, they may have their own hydrothermal systems. Studying vents in the Pacific is, in effect, studying what life on Europa might look like. NASA has even partnered with oceanographers to test technologies in the deep. Submersibles are treated as stand-ins for probes, and the difficulties of launching, controlling, and recovering them mirror the challenges of space missions. Instruments that measure chemistry, detect microbes, or capture images in darkness are refined in the ocean before being adapted for distant worlds. Even astronaut training has used underwater environments, with NASA's Neutral Buoyancy Lab and other underwater habitats serving as practice grounds for living in confined spaces, working in hostile conditions, and relying entirely on technology. One striking example is the Extreme Environment Mission Operations Program, or NEMO. For this, astronauts live in an underwater habitat off the coast of Florida, simulating life on a space station or another planet. They conduct experiments, perform simulated spacewalks, and adapt to the psychological demands of isolation. The ocean provides the perfect analogue, an environment where you cannot step outside unprotected, where communication is limited, and where every action must be planned carefully. It is space without leaving Earth. The ocean also prepares us for planetary science in another way, by revealing unfamiliar geology and chemistry. The landscapes of the deep are as strange as anything on Mars, towering chimneys of mineral smoke, volcanic ridges stretching for thousands of kilometers, trenches deeper than Mount Everest is tall. Learning how to study these features underwater helps prepare us for studying alien landscapes with rovers and landers. The methods overlap: mapping terrain, analysing samples, interpreting clues from environments we cannot touch directly. The practice we gain in the ocean makes us better prepared to interpret the data we receive from other worlds. Biology, too, benefits from this connection. Deep-sea organisms show us how life adapts to extremes: pressure, darkness, scarcity, and chemical toxicity. These adaptations expand our understanding of what life can be. When we consider possible alien life, we no longer limit ourselves to Earth-like conditions. Instead, we think about extremophils, organisms that thrive where others cannot. Bacteria in vents, shrimp in scalding plumes, fish in trenches. They become models for what might exist under Europa's ice, or within Enceladus's jets. Without the ocean, our vision of alien life would be narrower. With it, we see more possibilities. This connection between deep sea and space even shapes public imagination. When images of vents, glowing creatures, or submersible footage are shown, many people say the same thing. It looks alien. And that's because it is alien, at least to us. It is Earth, but it feels like another planet. That overlap between wonder and reality helps people imagine space in tangible ways. If we can discover such strangeness here, then surely strangeness awaits elsewhere. The ocean becomes a bridge between the known and the unknown, between Earth and the cosmos. NASA's collaborations don't stop with training or analogues. Some engineers are actively designing probes inspired by submersibles. Concepts for Europa landers include drills to pierce ice and submersibles to swim in the ocean below. Sensors tested in the Pacific may one day ride aboard these missions. Even the idea of autonomous fleets, robots that work together without human control, has roots in oceanography, where swarms of underwater drones are being developed to map and monitor the sea. The lessons cross freely between ocean and space, advancing both fields. It's not only about what we learn scientifically, but also about how we think. Exploring the deep sea forces humility. It shows us how little we know, how much resists us, how mystery persists despite our efforts. The same humility applies to space. The cosmos, like the ocean, is vast, and our knowledge of it is fragmentary. Both domains remind us that exploration is not about quick conquest, but about patient persistence. The sea trains us to accept that not everything will be answered quickly, that the unknown remains larger than the known. There's another reason NASA studies the deep: survival. The more we learn about Earth systems, the better we understand our own planet as a life-supporting world. Hydrothermal vents, carbon cycles in the twilight zone, chemistry in trenches, all influence climate, habitability, and planetary balance. Studying them doesn't just prepare us for Europa, it prepares us for Earth. In this sense, the deep sea is not only an analogue for other worlds, but also a mirror for our own. It forces us to see Earth as a planet among planets, dynamic and fragile. For explorers, the emotional parallels are just as strong. Astronauts describe the overview effect, the feeling of awe when seeing Earth from space. Ocean explorers describe something similar, the overwhelming sense of otherness when descending into blackness and encountering glowing creatures or alien landscapes. Both experiences shift perspective, reminding us that the familiar world is not as ordinary as we think. Both space and sea exploration expand our sense of belonging, reminding us that we live on a world full of places we do not yet understand. And so, when NASA studies the deep, it is not a diversion from its mission. It is part of its mission. To prepare for alien oceans, we must first understand our own. To design probes for Europa, we must first learn how to study vents on Earth. To imagine life beyond, we must study life below. The ocean becomes a training ground, a classroom, and a rehearsal for the future of exploration. Perhaps that is the greatest lesson of all. that alien worlds are not only out there, waiting across space. They are here, waiting beneath waves. To explore them is to bridge the distance between Earth and the cosmos, to practice for discoveries we have not yet made. The deep sea and space are not separate. They are reflections of the same desire, the same challenge, the same story of curiosity. When you imagine the ocean, you might picture waves crashing, gulls crying, or the roar of surf against rocks. But beneath the surface, especially in the deep, the ocean carries a different identity. It is not loud. It is not filled with constant sound. It is defined instead by silence, the kind of silence that feels heavy, layered, and infinite. A silence that conceals more than it reveals, that muffles human senses, and that turns the sea into one of the greatest keepers of secrets on Earth. The sound of silence in the ocean is not emptiness. It is a mask, one that has hidden both life and history for as long as we've looked across its surface without knowing what lies below. To understand this silence, you first have to think about how sound travels. In air, sound dissipates quickly, but in water, sound moves faster and farther. Whales can communicate across hundreds of kilometers. Submarines detect each other with sonar signals that echo for miles. And yet, for humans, diving into the sea feels almost mute. We aren't built to hear underwater, and what little we catch is muffled, distorted, or drowned out by the beating of our own hearts. To us, the deep ocean is silent because our bodies aren't tuned to its language. That silence creates mystery, because without sound, without vision, the ocean resists interpretation. The silence is also physical. Light cannot penetrate far, and so without eyes adapted to darkness or sensors designed for detection, we see nothing. The further down you go, the more total the absence becomes until you're left in blackness. Combine that with our inability to hear, and the deep ocean becomes a place of profound concealment. It hides in plain sight, not because it is empty, but because it surrounds us with conditions that strip away our senses. Silence, in this context, is not the absence of noise. It is the absence of human access. For centuries, this silence allowed myths to flourish. Sailors spoke of sea monsters, ghost ships, and bottomless pits, not because they saw them clearly, but because the ocean gave them no evidence to contradict imagination. A ripple, a shadow, a shape in the fog, all became amplified by the silence below. The sea's refusal to reveal itself created space for legends. In a way, the silence was complicit. It allowed stories to grow unchecked, because the truth remained buried too deep to see or hear. In the modern era, we've pierced that silence with technology. Sonar sends pulses of sound that bounce off the seafloor, revealing shapes. Hydrophones record the clicks, songs, and moans of whales, revealing communication on scales we never imagined. Submarines, both military and scientific, use acoustic systems to navigate in places where GPS cannot reach. We have discovered that the silence is not absolute, but filled with layers of sound that simply escape our ears. But even with these tools, much remains hidden. The ocean still keeps its secrets, not through complete silence, but through silence relative to us. We can only interpret fragments. What's most remarkable is how this silence conceals life. The twilight zone, the abyss, the trenches, all are filled with creatures adapted to darkness. But without sight or sound, we missed them for centuries. Only when machines descended did we find glowing fish, transparent shrimp, and otherworldly jellies. Without lights and sensors, they remained invisible, hidden behind silence. Even now, we suspect that countless species remain undiscovered, not because they are rare, but because silence conceals them from our crude instruments. The ocean hides not by emptiness, but by overwhelming us with its refusal to translate. The silence also preserves history. Wrecks lie for centuries without disturbance. Cities drowned by rising seas vanish without trace. Bones, artifacts, and entire landscapes remain untouched, sealed in quiet. On land, ruins weather and collapse, But underwater, silence protects. The absence of waves, air and light creates a vault where time slows. When explorers discover amphorae still stacked in an ancient ship, or boots lying untouched on the deck of a sunken warship, they're seeing what silence has preserved. The ocean hides, but in hiding, it keeps memory intact. But silence is not always protective. Sometimes it is threatening. Submarines use it to vanish, slipping below sonar detection, turning oceans into fields of strategic secrecy. Scientists searching for whales sometimes lose track of entire populations. Their calls swallowed by vast distances or masked by background noise. Fishermen once believed species were abundant, only to discover too late that silence hid decline. What the ocean does not reveal quickly becomes invisible to us, and invisibility breeds misunderstanding. One of the most profound encounters with oceanic silence came during the Cold War. Navies deployed arrays of hydrophones to listen for submarines, building networks that spanned entire oceans. But these systems also picked up other sounds, whale songs echoing for hundreds of kilometers, strange booms and rumbles, even unexplained signals scientists still debate. What began as military secrecy revealed biological richness. The silence was not absence at all, but presence we hadn't noticed. Whales, once thought solitary, turned out to sing across oceans. Earthquakes rumbled beneath trenches. Icebergs cracked and groaned. The ocean spoke all along. We just hadn't been listening. Still, silence remains the ocean's dominant character. For every sound detected, there are countless things unheard. For every image captured, millions remain unseen. The sea's ability to hide is unmatched. Even space, vast as it is, reflects starlight and reveals galaxies. The ocean does not. It swallows light, it muffles sound, and it guards its interior with density and pressure. Silence here is not passive, it is active, a force that protects mysteries from casual discovery. For explorers, this silence is both obstacle and allure. It frustrates because it limits what we can know, but it also compels because what is hidden promises revelation. Every descent, every new hydrophone, every sonar sweep is an attempt to pierce the mask. And every time we succeed, we glimpse how much more remains behind it. The silence reminds us of scale. It reminds us that human senses are limited. It reminds us that the planet is deeper, stranger, and more complex than we assume from the shore. Perhaps that is the ocean's greatest secret, that silence itself is a strategy. By hiding so well, it forces us to slow down, to work harder, to remain humble. It keeps mystery alive in a world where mystery often feels diminished, and in doing so it shapes not just science but imagination. Writers, filmmakers, dreamers, they all return to the ocean as a source of wonder because it withholds as much as it gives. Silence is not emptiness, it is potential. And so, when you think of the ocean hiding secrets, don't picture a blank void. Picture instead a vault. Inside are creatures glowing unseen, wrecks resting intact, landscapes from ages past, and processes that shape Earth itself, all of it held behind walls of silence, waiting for the rare moments when technology, persistence and chance align to reveal a fraction of what lies within. The silence is not something to break, it is something to respect. It has kept the ocean's mysteries safe for millions of years, and it ensures there will always be something left for us to discover. Long before sonar, submersibles, or remotely operated vehicles, people already knew the ocean was a place of secrets. They couldn't measure its pressure or map its trenches, but they could see its vastness and feel its unpredictability. And where knowledge failed, imagination took over. From that imagination came myths and monsters, stories of creatures so immense or so strange that they blurred the line between fear and fascination. For centuries, sailors and coastal peoples filled the silence of the deep with krakens, mermaids, leviathans, and sea serpents. These legends weren't just entertainment, they were attempts to explain an ocean that refused to explain itself. One of the most enduring figures is the Kraken, a giant cephalopod said to lurk in northern seas. Sailors told stories of ships being dragged beneath waves by massive tentacles, their crews swallowed into the dark. Drawings from the 17th and 18th centuries show enormous creatures rising from the water, wrapping entire vessels in their arms. To modern eyes, these accounts read like exaggerations of encounters with real animals, perhaps giant squids, or even pods of whales mistaken in the chaos of storms. But to sailors of the time, they were serious warnings. The ocean already took ships through storms, reefs and currents. To add an unseen monster to its arsenal made it feel all the more threatening. The Kraken became a symbol not only of fear, but of the incomprehensible scale of the sea itself. Mermaids tell a different kind of story. Unlike krakens, they were not usually monstrous, but alluring. Half human, half fish, they appeared in myths across cultures, from the sirens of Greek lore who lured sailors to their doom, to the selkies of Scottish tales who shed their sealskins to become human, to the ningyo of Japan, creatures whose flesh was said to grant long life. The consistency of mermaid legends across continents suggests something deeper, a human desire to see ourselves in the sea, to imagine kinship with what lies beneath. Where krakens represented terror, mermaids represented connection, though often laced with danger. To encounter one was to cross into a liminal space between human and ocean, reality and myth. Sea serpents also haunt history. Reports of long, snake-like creatures writhing across waves appear from Scandinavia to New England. Some accounts describe creatures dozens of meters long, with heads like horses and bodies that moved like chains of barrels. Skeptics today suggest sightings of oarfish, enormous but slender fish that can grow more than 10 meters long and occasionally rise near the surface. Others point to misidentified whales or giant eels. But the persistence of sea serpent stories speaks less to zoology and more to psychology. People needed a way to give shape to the unknown, and serpents, already symbols of danger in many cultures, fit easily into the blank canvas of the ocean. These myths weren't born only from mistakes. They were fueled by the ocean's silence and its ability to hide. A glimpse of a fin, a flash of light, a shadow beneath waves. These fragments were enough to spark entire legends. In the absence of certainty, imagination filled the gaps. And because the ocean resisted confirmation or denial, myths endured for centuries, repeated in taverns, written in logs, illustrated in books and believed by generations. Monsters also served practical purposes. They warned sailors of dangers, reinforced caution, and explained disasters. A ship lost in a storm might be said to have been taken by a kraken. A drowned fisherman might be blamed on mermaids luring him into the sea. These explanations softened the incomprehensible, giving names to tragedies that otherwise felt random. They also gave shape to respect. The ocean was not to be underestimated. It was a realm with its own rulers, its own creatures, its own power. To tell stories of monsters was, in a sense, to acknowledge the limits of human control. Even today, echoes of these myths remain. The giant squid, once thought to be pure legend, turned out to be real, though less ship-destroying than imagined. The first photographs of a living giant squid in the early 2000s and later the first videos felt like a moment when myth and science shook hands. The creature existed, but not exactly as described. It was stranger in some ways, with enormous eyes adapted to the deep and tentacles lined with hooks. It didn't drag ships beneath the sea, but it was still enormous, still alien, still proof that myths often grow from kernels of truth. Mermaids, too, find echoes in real animals. Some historians suggest that sightings of dugongs or manatees may have inspired stories. From a distance, especially in poor conditions, these animals might appear vaguely human-shaped as they surfaced. A lonely sailor far from home might project familiar forms onto unfamiliar animals. Over time, those fleeting impressions could crystallize into tales of half-human beings. The truth may not be glamorous, but it shows how myths can grow from the human tendency to see ourselves in the world around us. What makes myths and monsters fascinating today is not whether they're real in the literal sense, but what they reveal about us. They show how we respond to mystery, with fear, with imagination, with storytelling. They show how silence invites voices, how absence invites invention. And they show how the ocean has always been more than water and waves. It has been a mirror for human psychology, reflecting our hopes and our fears in equal measure. Science hasn't erased these stories, it has reframed them. When we watch a glowing jellyfish pulse in the dark, it feels no less magical than a mermaid's song. When a whale surfaces and its call echoes across miles, it feels no less awe-inspiring than the cry of a leviathan. The monsters may not exist exactly as told, but the sense of wonder they inspired remains intact. In some ways, the real ocean is more incredible than the myths. Its creatures glow with their own light, withstand crushing pressures, and migrate in numbers that dwarf any land migration. Its landscapes are stranger than anything drawn on old maps. Science doesn't remove mystery, it deepens it. Yet the myths endure because they speak to something timeless. Even now, in an age of satellites and sonar, people still tell stories of unidentified creatures seen at sea. The Loch Ness Monster continues to inspire fascination despite decades of searches. Fishermen still return with tales of shapes too large, too strange, too fleeting to explain. Perhaps these stories will never die because they answer a need. We want the ocean to hold secrets. We want it to be bigger than us, stranger than us, beyond us. Monsters, whether real or imagined, guarantee that it remains so. And so, from krakens to mermaids, from leviathans to serpents, the ocean's myths remind us that the line between reality and imagination has always been blurry. The silence of the sea, the fragments we see and hear, the fear of the unknown, all combine to create stories that endure long after ships return to port. These myths may not describe actual creatures in their full detail, but they describe something equally real, the feeling of standing before a mystery too vast to resolve. The monsters are in that sense symbols of the sea itself. When people talk about the future of exploration, they usually look up. Telescopes scanning the stars, rockets heading for Mars, dreams of colonies on distant worlds. But while eyes turn skyward, another frontier waits quietly below, far closer, far less understood. The future of discovery is not only written in space, it is written in the sea. Mapping the unknown here, in the vast depths beneath us, is a challenge as profound as charting galaxies, and perhaps more urgent, because it is the foundation of the world we live on. At this moment, most of the seafloor remains unmapped in detail. Satellites can measure the shape of the ocean's surface, which reveals broad outlines of what lies beneath. But those maps are rough, accurate only to a scale of kilometres. To put it simply, we know the surface of Mars better than we know the bottom of our own ocean. Less than a quarter of the seafloor has been mapped with high-resolution sonar. The rest is a blur, a suggestion, a blank space waiting for lines and details. For a planet we claim to know, this ignorance is astonishing. Mapping matters because without it, we're guessing. We guess where trenches run, where seamounts rise, where faults spread. We guess where resources lie, where ecosystems gather, where hazards threaten. Every voyage of a research ship adds a piece to the puzzle, but the puzzle is immense. The task is not simply to make maps for the sake of maps. It is to understand Earth's skeleton, the frame that shapes its oceans, climates, and life. The deep sea is not background, it is structure. To map it is to see the architecture of the planet revealed. Technology is already advancing toward this goal. Multi-beam sonar systems send out fans of sound waves that sweep the seafloor, returning echoes that create detailed images. Autonomous underwater vehicles untethered and free to roam, carry these systems deeper and longer, covering ground that ships cannot. Swarms of small drones are being imagined, fleets that could work together, scanning vast areas like bees pollinating a field. Satellites may never see through water, but combined with sonar and drones, they help focus efforts, guiding where exploration should go first. Piece by piece, the blur sharpens. The scale of the challenge is daunting. The ocean covers 70% of Earth, with an average depth of 4 kilometres. Mapping it all with precision would take decades of continuous effort, fleets of ships, thousands of missions. That's why international collaborations are emerging. Projects like Seabed 2030 aim to map the entire seafloor by the end of the next decade, pooling data from ships, navies and private companies. It is a monumental goal, but one that reflects a growing recognition. The deep sea cannot remain blank forever. It is too important, too influential, too connected to leave unseen. What might we find when the maps are complete? Almost certainly new seamounts, perhaps tens of thousands of them. New trenches, ridges and volcanic systems. New vents, oases of life thriving without sunlight. Possibly even evidence of drowned landscapes, traces of human history lost to rising seas. Every detailed map brings surprises, because the seafloor is not static. It shifts, erupts, and grows, reshaped by tectonic forces as alive as any weather system above. To map it is not just to reveal terrain, but to reveal process, to see Earth as a planet still in motion. Mapping also matters for safety. Tsunamis are born from undersea earthquakes, and their size and impact depend on seafloor shape. Submarine landslides, triggered by quakes or erosion, can send walls of water racing across oceans. Without accurate maps, predictions remain rough, warnings less precise. Mapping the seafloor isn't only about curiosity, it's about protecting coasts where billions of people live. The more we know of the shape beneath the waves, the more prepared we are for the hazards above them. The future of mapping will also deepen our understanding of life. Most marine species live near the seafloor, and ecosystems depend on its contours. Canyons funnel nutrients, seamounts concentrate currents, ridges create turbulence that stirs food upward. Without knowing the geography, we can't understand the biology. Every new map becomes a guidebook for future discoveries, pointing us to places where strange creatures might thrive. If we want to know how much life the ocean holds, where it flourishes, and how it sustains the planet, maps are the starting point. Some worry that mapping will also reveal resources, minerals in nodules, metals in crusts, energy in vents that could trigger exploitation before we understand the consequences. This is the double-edged nature of discovery. To see is to know, and to know is to tempt use. But hiding ignorance does not prevent exploitation. Companies already eye the deep sea, and without maps, decisions will be made blindly. Better to know, and then choose wisely, than to remain blind and stumble into harm. The future of mapping, therefore, is not only scientific, but ethical. It will force questions about what we value more, profit or preservation. For explorers, mapping represents a paradox. On one hand, it reduces mystery. Blank spaces on maps have always fueled imagination, and filling them risks diminishing that. On the other hand, each new detail adds new wonder. When the Titanic was found, it didn't end its mystery, it deepened it. When vents were mapped, they didn't end curiosity, they expanded it. The ocean will never lose its secrets entirely, because every answer opens new questions. Maps don't close mysteries, they multiply them. The tools of mapping will only grow sharper. Advances in artificial intelligence promise faster processing of sonar data, turning raw echoes into clear images in real time. Robotics will allow continuous missions, machines roaming for months without return. Energy harvesting from currents may one day power long-term observatories on the sea floor, sending back data continuously. What we imagine now as occasional glimpses may soon become constant vision, a living map updating itself as the ocean changes. Yet even with all these advances, one truth will remain. No map can capture everything. Just as a street map cannot convey the life of a city, a seafloor map cannot capture the complexity of ecosystems, behaviours and interactions. The future of discovery will require more than lines and shapes. It will require dives, footage, samples, and above all, patience. Maps are the beginning, not the end. They are the framework upon which exploration builds. Perhaps the greatest promise of mapping the unknown is perspective. We live on a planet where most of the surface lies hidden, yet we act as though we know it. Filling in those blanks will remind us of scale, of humility, of how much still waits beyond reach. It will remind us that exploration is not a closed chapter of human history, but an ongoing story. And it will remind us that the greatest mysteries are not always in the stars, but here, in the depths we pass over every day without noticing. The future of discovery, then, is not about conquering the ocean. It is about listening to it, revealing its contours, and understanding how they connect to life and climate and history. It's about treating the ocean not as background but as foundation, and it is about admitting that our planet still holds frontiers worthy of wonder. To map the sea is to map ourselves, our home, our place in the universe. The unknown waits below, and the tools to reveal it are finally in our hands. After travelling through the deep sea in thought, drifting past trenches and plains, glowing creatures and lost wrecks, it feels natural to ask what it all amounts to. We've looked at landscapes hidden beneath miles of water, listened to how the ocean resists us, and followed machines into places no diver could ever survive. And yet, even with everything revealed, the ocean still feels like a mystery. Maybe that's the point. Maybe the value of the deep sea is not only in what it contains, but in the fact that it refuses to give everything away. Mystery itself becomes part of the lesson. Human beings have always been uneasy with the unknown. We build maps, write explanations, design machines, and fill gaps with stories. It makes us feel secure to know where we are and what surrounds us. The ocean has always resisted this impulse. From the first time people set out in boats, they knew they were moving across something vast, unpredictable, and dangerous. Storms could erase them, currents could pull them away, creatures could appear suddenly out of black water. That resistance to certainty gave birth to myths and legends, but it also gave birth to curiosity. If the sea had been shallow, small and transparent, it would never have inspired the same intensity of imagination. Its vastness forced us to wonder, and that is where its power lies today. Even in an age of satellites, global communication and exploration that has reached other planets, the ocean reminds us that not everything is known. The deep keeps its silence, its pressure, its endless blackness. It doesn't yield easily. We send submersibles and robots, and they return with breathtaking images, but those images are fragments, brief windows into something far larger. What we know only grows as fast as the machines can capture it, and what remains unknown always outpaces them. That imbalance is not a weakness, it's what makes the ocean endlessly compelling. Mystery matters because it keeps imagination alive. When sailors saw shadows and invented krakens, they weren't just telling stories, they were acknowledging their limits. Today, when scientists glimpse a new species in the beam of an ROV, they too are acknowledging limits. The deep tells us, again and again, that we are not finished with discovery. Every layer of mystery left intact fuels the next generation of explorers, writers, dreamers, and scientists. Without mystery, curiosity dries up. With it, curiosity becomes endless. Mystery also creates humility. We often behave as though Earth is small, as though we've mapped it, measured it, and catalogued it. But the ocean proves otherwise. It reminds us that most of the planet is beyond our daily reach, beyond our control, and beyond our comprehension. To recognise that is not defeat, it is perspective. It places humanity back into scale, showing us that we are participants in a world far larger and older than ourselves. That humility is valuable, especially in an age when human influence reaches even into the trenches. The sea shows us both our reach and our limits. There's also a practical reason why mystery matters. Unknown does not mean irrelevant. What lies beneath waves influences climate, shapes continents, sustains life, and even preserves history. The carbon cycle depends on creatures we've never named. The balance of heat across the planet depends on currents that flow through valleys we've barely mapped. Medicines, proteins, and ideas for technology may come from organisms glowing quietly in the abyss. To treat mystery as unimportant would be to ignore the systems that sustain us. Discovery is not optional. It is survival. But discovery without mystery becomes mechanical. If we knew everything, exploration would feel empty. The deep sea avoids that fate by always staying one step ahead. Each answer uncovers new questions. Each new map reveals new blanks. Each dive uncovers not completion but expansion. This endless cycle keeps exploration alive, and it keeps wonder alive too. Mystery ensures that the future will always hold something worth seeking. Think of the experience of looking at the stars. Even with telescopes and physics, the night sky still feels mysterious. That mystery doesn't diminish science, it enriches it. The same is true for the sea. When submersibles capture footage of bioluminescent creatures, the science is precise, but the effect is wonder. When sonar maps trenches deeper than Everest is tall, the data is clear, but the feeling is awe. Mystery and knowledge don't cancel each other. They sustain each other. The more we know, the more we realise how much remains. There's also something deeply human about needing mystery. Our stories, myths, and even our sciences have always grown out of questions we couldn't yet answer. Remove the mystery and you remove the spark. The ocean ensures we never lose it. It gives us both answers and gaps, enough to learn but never enough to finish. In that way, it's not just an environment, it's a partner in our own growth. In the end, the question isn't whether we'll solve the deep sea completely. The question is whether we should even want to. Complete understanding may not be possible, but perhaps that's not the goal. Perhaps the goal is to continue learning, to keep being surprised, to preserve mystery as a vital part of being human. The ocean is not a problem to be solved, but a conversation to be continued. When explorers return from dives, they rarely speak in terms of final answers. They speak instead of glimpses, strange creatures drifting past, landscapes that look like alien planets, sounds they cannot explain. Those glimpses feed not only research papers, but also stories told to families, images that inspire children, and ideas that spark future inventions. The value of mystery is not that it stays hidden, but that it invites us to keep looking. And so, after all the journeys through pressure and silence, through wrecks and myths, through machines and maps, what remains is not a sense of closure but of continuation. The deep sea will not run out of secrets. It will not stop resisting. It will not stop concealing. And because of that, it will not stop inspiring. The final reflection is simple. Mystery matters because it keeps us alive to wonder. Without it, the world shrinks. With it, the world stays vast. The ocean ensures that vastness is always with us, right here on Earth, waiting beneath the waves.